Hello, everybody. Welcome to the October 2021 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. And greetings from sunny Boston, Massachusetts, where I remain for my visit here to the Harvard Philosophy Department. It is sunny actually at this exact moment, but as cliche as it is, what I have to comment on is the weather here in the northeastern United States. Because, I live in Los Angeles and have for the past 15 years or so, where it's sunny and dry almost all the time and the right temperature. And actually, I've been blessed with the right temperature pretty much here in the Northeast, but boy, is it humid. And I say this as someone who lived in Boston for 8 years and before that in Pennsylvania for many years. But I kind of forget that 75 degrees in the Northeast is just not the same weather as 75 degrees in Los Angeles. That's about it for my deep insights here, because I've mostly for the past month been just concentrating on getting books written and other things that I've had to do, revising papers and writing letters of recommendation. It's that part of the year. Doing a tiny little bit of traveling, not too much. So yeah, no real big news other than that. So with that spirit in mind, let's go. Falcoretto says, great podcast on paleogenetics. Toward the end of the discussion, the idea of kickstarting life processes on other planets came up. Do you think we are or ever will be wise enough to evaluate and take that step? We do not have a good track record on such past intrusions, despite whatever good intentions may have been in play. Well, you're absolutely right. We do not have a good track record. By we, I mean the human race generally. And the question that came up for those of you who didn't listen to the podcast, this is with Bergsonian Chore. We talked about the idea not of starting life on other planets, but basically of if there were other planets. We're imagining very far into the future, where we're visiting planets around other star systems, for example, although you could imagine the same question for the solar system. What if there's no life wherever we are visiting and looking? We decide that, not Mars, let's say, but some moon of Neptune has no life on it, but it could have life for whatever reasons. We can imagine forms of life that might live there. Would we be tempted to put the raw materials to start life into that environment, to let it go its own way? In some sense, that's a minor intervention. We're not, changing a society or anything like that, or even seeding a planet with life or terraforming it, but we're just giving it some raw materials it didn't otherwise have. So let me first say, before answering the question, I agree that our intentions are not always as good as they could be. Even when we have good intentions, we don't always do well at following through. But also, my attitude toward many of these questions, by these questions I mean, should we human beings indulge in this amazing thing that technology will someday allow us to do? My attitude toward these questions is, look, we're going to do it, right? There's no question about whether we're going to do it or not. Human beings, whatever their track record is for having good or bad intentions, their track record for doing what they're capable of doing is almost 100% we do it, right? We dropped atomic bombs on cities full of people. That's how human beings roll. When we derive some new technological capability, no matter how horrific the consequences, we do it. So whether it comes to designer babies or uploading consciousnesses or seeding other planets with the raw ingredients for life, I think that our expectation should be that we're going to do it. Now, but actually in this particular case, I don't think it's that bad. I haven't thought through all the details very, very carefully. So you might be able to change my mind about this without too much effort. But if there's literally no life on a planet, and we're sure of that, whatever it means to be sure of that, I don't see the harm in putting the raw materials of life onto a planet. Indeed, I wouldn't really see the harm in putting life onto the planet. Certainly we're not going to have that many qualms about visiting and setting up human habitation on other planets. Probably, I don't think. That doesn't mean we should sort of despoil the entire galaxy or the entire universe, whatever. There can be limitations on what we do. But if it's literally another planet that doesn't already have life on it, I don't see the harm. I don't see literally who is being harmed by us doing some dramatic intervention to it. I do think we need to be careful about it. It's so far from our experience that it's hard to think through all the consequences very clearly. But nevertheless, I suspect it's going to happen, and I'm kind of okay with that. Peter Bamber says, about half of marriages in the USA and in the UK end in divorce. The promise to stay together until death do us part appears to be nonsense in many cases. Should marriage be a time-limited contract, perhaps a renewable rolling contract? What use is marriage? All right, someone wants to get their money's worth with the AMAs here. This is a big question, right? And I don't have any simple answers to this one either. That's probably going to be a theme through this AMA. I'm in favor of marriage myself. I am in one, which is extremely successful. That doesn't mean it's for everybody. I'm perfectly cognizant of the fact that for some people, marriage is wrong, even for some people who get married. It's certainly true that people do also get divorced. Now, you could imagine just confessing to that, right? Admitting it. That, in other words, stopping pretending that marriage is forever. This is probably what you're getting at. I would be 100% on board if you said that we could introduce into the institution of marriage different levels, right? Different kinds of commitment. Some people might say, well, we're going to get married for 5 years. Other people might say, we're going to get married till death do us part. Either one is sort of allowed and written into the contract. I can imagine that. But I suspect that most people would just want to do it till the death do us part. So to me, the more important thing is to have a mechanism, is for the mechanism to end it be a lot easier and simpler and more straightforward than it actually is. You know, the rules are complicated. Divorce tends to create bitterness and financial strife and a whole bunch of things like that. I think that, in fact, we have some feeling that divorce is somehow bad, and therefore, if you're going through it, you should suffer. You know, it should be difficult to go through it. And I'm against that. I think it should be a lot easier than that. And obviously, I think that if only one person wants to get divorced, that should more or less be enough. I don't think that you should be able to force someone to stay married to you. Now, you ask what use is marriage, and I think that's a very good question because there's more than one use that people have in mind, right? I mean, there's the sort of romantic role that marriage plays as a commitment to another person. I think that's a good thing. Again, not for everybody, but for some people, it's the right thing. I'd be very open to also not just imagining more flexibility in the institution of marriage in terms of the time horizon that we attach to it, but also the structure. You know, I'm very happy to imagine group marriages, obviously gay marriage or whatever. I think I'm 100% fine with that. Maybe there could be, you know, if you read The Moon is a Harsh Mistress by Robert Heinlein, there's all sorts of elaborate marriage structures like line marriages where there's a whole group marriage, and when someone dies, someone else is brought in, right? And the line marriage can last for centuries, you know, who knows? Do you call that a marriage or not? You see, I think those things are much more difficult to make work in practice than in theory, but that's okay. If it works for at least one group, that should be enough as far as I'm concerned. Anyway, I was trying to say that there is a romantic reason for marriage, and I'm all in favor of that. There's also a legal reason, and I suspect that a lot of the weirdness about marriage in the modern world is because these are two very different uses, the romantic use and the legal use. And the legal use is not to be taken lightly. Like, in fact, it's a really, really good reason for a lot of people to get married. I have friends who are not married, even though they are absolutely, completely bonded and have been for many, many years and will be for many, many years into the future. And I worry about that a little bit because in our modern world, if you're married to somebody, then your spouse has all sorts of rights automatically. Most importantly, when one member of the marriage is ill or dying or died, the legal control over what to do goes to the other person in the marriage. And so that is an incentive to get married. Absolutely. 100%. And maybe that should be separated from the romantic role. I'd be open to that possibility. But there has to be some equivalent of that. And I think that would be very important. So I'd be open to imagining sort of the institution of marriage being one thing and being entirely romantic, and then other sorts of legal obligations and connections on the market that one could pursue. That might be a more enlightened way to do things. But, you have to deal with the fact that in the real world, people are not that enlightened, and people have strict ideas handed down through generations about what marriage should be. So I don't see any of this actually, or much of it anyway, happening very soon. Seumas, I don't know how to pronounce your name, sorry. Seumas McLennan. Is it supposed to be Seamus? Mistyped? I don't know. Says, as a non-physicist, I think I can get a bit of a handle on a number of concepts and models in physics via analogy, diagrams, simpler equations, and such. But the idea of a singularity leaves me stumped. Is singularity just a formulation of our ignorance, or can it be imagined as a thing with a knowable nature? I think that the word singularity appears in different contexts in different physics situations, most famously in general relativity, Einstein's theory of curved space-time, where a singularity is a place where the curvature of space-time becomes infinitely big, roughly speaking. There's different kinds of singularities. There's whole books written classifying different kinds of singularities. But singularities also appear in other contexts, such as fluid mechanics or, field theory sometimes. And usually, the way that a professional physicist thinks about a singularity is as a place where your theory is breaking down. So I know that we like to talk a lot about what happens at a singularity, blah, 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 but you have to understand that when physicists say those words, what they really mean is what is happening in nature at the location or at the time when our theory is predicting a singularity. So the more precise formulation is not what happens at a singularity, but what happens instead of a singularity. So I wouldn't spend too much time worrying about singularities, actually. And I've had this discussion with, people who do classical general relativity or philosophy of space-time or things like that, who sometimes just spend a lot of work thinking about classifying singularities, dealing with them, predicting them, etc. And my attitude is, but they almost certainly don't happen in nature, so why are you doing that? You're figuring out implications of a theory in the regime where the theory is not accurate, so that's not really what I personally want to spend my time doing. Spoonly Orange says, you say in the Biggest Ideas Q&A number 21 episode, where you discuss the emergence of spacetime from Hilbert space, that gravity enforces a kind of limit on the dimensionality of Hilbert space. Does this mean gravity has a direct effect on Hilbert space, and would that be considered, would gravity therefore be considered more fundamental? I'm not quite sure what the question is asking, and would be considered more fundamental than spacetime. So I think that the logic is a little bit not exactly how I would put it there. I don't think that it would be right to say gravity has a direct effect on Hilbert space. The right way to say it is gravity as a phenomenon in the form that we know it, in the sort of general relativistic form where it shows up as the curvature of space-time, should be thought of as something that arises in Hilbert space theories where Hilbert space itself is finite dimensional. So the Hilbert space is always more fundamental than space-time or anything like that, at least in my way of thinking about it, which is, it's my AMA, so I'm going to go with that right now. Hilbert space is where you start. So you don't say gravity has an effect on Hilbert space. You say the following kinds of Hilbert spaces can support theories of gravity. Other kinds of Hilbert spaces do not. And I think that infinite dimensional Hilbert spaces typically will not have gravity, or at least it will have gravity in a form where local regions of space-time still look like they're only part of the whole Hilbert space. They're described by a finite dimensional piece of Hilbert space. So, for example, the anti-de Sitter space conformal field theory correspondence, the holographic duality that string theorists like to talk about, has the following feature. The boundary theory, which is a conformal field theory, no gravity, okay? It has an infinite dimensional Hilbert space. No question about that. And it also is supposed to correspond to a quantum gravity theory in anti-de Sitter space, okay? An anti-de Sitter space is infinite in spatial extent. So if you think that so that's compatible, in other words, in the following way. in the anti-de Sitter space, where there is gravity, you can say that every region of space is described by a finite dimensional piece of Hilbert space, but there are an infinite number of pieces. That's how you're allowed to correspond to the infinite dimensional Hilbert space that is on the boundary. So the gravity theory as a whole has an infinite dimensional Hilbert space, but the individual spatial regions are only a finite dimensional piece of them. Riverside says, you interview scientists coming from around the world that do amazing work at American universities, yet at the same time, the United States seems to have become a rather anti-scientific country over the last years. Some may say that the American brand of radical free market capitalism is driving both trends, the fast-paced scientific innovation and the deep economic divides in society that make people prone to populism and mistrust towards science, rationality, and democratic procedures. Would you see it this way, and is improvement possible? I think, there are ingredients that you have identified that play parts, that play a role in this syndrome. But I do think it's very, very complicated, and I wouldn't want to buy into any overly simplistic way of thinking about it. For one thing, I don't even know that it's true that or accurate to say the United States has become a rather anti-scientific country over the last years. This complaint that the United States is anti-scientific or anti-intellectual or whatever is a perennial complaint, okay? It's been going on for a very, very long time. When I was just starting out, the big controversy was over creationism in high schools, okay? And nuclear power, that was another big controversy where, again, and even before that, there was, the 60s and sort of folk spirituality and things like that. And all of these got complaints that they were being anti-scientific. So I don't know of any objective way to measure how anti-scientific we're being and whether or not it has in fact increased over the past several years. Okay, so having said that, I should also say I don't know how to measure whether or not the United States is more anti-scientific than other countries or than other scientifically industrialized countries or anything like that. So these are impressions, but these impressions, I don't trust them necessarily. I mean, maybe they're true. I'm not saying they're not true. I just don't know how to test them in a value-free, objective way. Okay, but there's still a question. There is anti-scientific sentiment, and where does that come from, right? I mean, whether it's more or less here or now than in other places or times, I don't know, but it's there. So where does it come from? And I think it comes from a lot of different places. And, even though I just said don't be too simplistic about it, let me give you my very, very simplistic take on one aspect that I think is overlooked, okay? You suggest capitalism as a possible cause, and again, maybe that's true, but I want to emphasize the role of culture in this one, the ideas role rather than the money role, because when you go back to, as I said, the debates over creationism in public schools, for example, I think that scientists were continually frustrated when they were trying to argue against teaching creationism in schools because they were arguing on the scientific merits. They were saying, here are the pieces of evidence we have for Darwinian evolution and for change of species over time, et cetera, et cetera. Therefore, we should teach this correct theory in the schools rather than some incorrect theory. But I don't think that for most people who are on the other side, I don't think that was the point. I'm sure that for some people who are on the creationist side, they really just looked at the evidence and came down on that side. But I think that for a large number of people, there were cultural issues at work. In particular, resentment issues. We're more familiar with that these days in the populist era than we did have in the discourse in, let's say, the 1980s, where I'm thinking of. But it was still there, when you have a big heterogeneous country like the United States, and that's why there might be some American exceptionalism here. The United States is bigger than most countries. Its population is largely non-native. Right? I mean, the people who are in the United States today are, the overwhelming majority of them, not descended from families who were here in the United States 500 years ago, right? They came from a whole bunch of different countries, bringing different traditions and cultures along with them. And the history within the United States is complicated, especially by things like the Civil War. So we have regional differences. Some regions had slavery, some did not. And so all of these things mean that there's a wide spectrum of kinds of people living in the United States, perhaps a wider spectrum than in most other countries. Even other big countries like India or China, big population-wise, they have more of a common history than the United States does, if we're thinking about history stretching over 500 years, 1,000 years, etc. So what that means is that, even though the United States is a country and has its history, not everyone necessarily identifies with the rest of the country or with other parts of the country. And so, again, to be very simplistic about it, and I would like to see data here too, and so you're welcome to check me, but my feeling is that subpopulations of people in the United States tend to be a little bit ornery about being lectured to by other subpopulations, okay? Whether it's, economic class or geographic location or cultural history or whatever, people don't want to be told what to think and how to believe and what to do. And so I think that for a lot of people, to go back to creationism, this is the point I'm trying to make, for a lot of people, the desire to get creationism taught in schools was not really about creationism. It wasn't even really about religion. It was about asserting the right to determine for themselves what they wanted taught in their local schools, rather than being told by some government bureaucracy or some academic elites or even some group of scientists what to be taught in their schools. So when the scientists came in and said, "Let me explain to you the truth," this was counterproductive. This is exactly what they were reacting against. So, and I think similar dynamics are at work with anti-scientific movements in the United States today. Kyrie Irving, the basketball player, okay, is on the record saying that he believes that the earth is flat. And he got laughed at for doing this. But he got a little bit of a platform because he's a famous and very talented basketball player, okay? And why in the world would anyone believe that the earth is flat? This makes no sense scientifically. And I take it as a sort of a signaling effort to say, whatever you authorities are going to tell me to believe, I'm not going to believe them. I'm going to be skeptical. I'm going to do my own research, right? Do these phrases sound familiar to you in this day and age? So the question to ask when someone says, I believe the earth is flat, or the attitude to take, the strategy to take, is not, let me assemble for you the pieces of evidence that tell you that the earth is not flat. That's just the entirely wrong thing to do. The thing to do is to say, what makes you believe that? What is it about the traditional scientific story for which there is overwhelming evidence that makes you distrust it? And so I think that if we wanted to decrease anti-scientific sentiment in the United States, and this is something I'll talk about in future podcast discussions, we really need to think about empowering people and making them feel like they're not being told what to do and what to think and what to believe by people who are out of touch with them. That's a bigger project. I'm not sure how to do it, but that's my simplistic theory to address that question. Robert Ruxandrescu says, the question is, how can you reconcile the instantaneous integrated conscious experience of your brain with a space-like separated structure? So the point is, and Robert goes into a greater detail if you want to look at the question in the AMA, but you have a bunch of neurons in your brain, and we attribute to that collection of neurons firing signals at each other something we call consciousness, right? But even though neurons are fairly close together, they are still space-like separated at any one moment of time. That is to say, a neuron on one side of your brain will require some time to send a signal to the other side of your brain, even if that signal moves at the speed of light, which it doesn't quite. They always move slower than the speed of light. So in what sense can we attribute an instantaneous notion of integrated conscious experience? And I think the answer is it's a mistake to take too literally the idea of instantaneous integrated conscious experience. There is no such thing. The human brain works at a certain set of time scales, and actually different parts of it work at different time scales, but none of those time scales is instantaneous. We think about the world, we perceive the world in a coarse-grained way, and time is included in that. It's not that there's any discretization of time, but we sort of smear out what we think of as one moment of time into some finite interval, which might be very small, so small that we don't even notice it. But it's just not true that we need to think about instantaneous interactions in the way that a physicist would seriously take that to make sense of what the brain is trying to do. The brain is only approximately instantaneous, and that's only on human scales, not on physics scales at all. I'm going to now group two questions together. One is from James Nancaro, who says, I'm puzzled by your conclusion about the fundamental origin of the universe and wonder if you could discuss this further. You had a whole podcast on why there is something to nothing. You don't have an answer in that podcast except to say the universe just is. You seem to give Tegmark's idea, and any other idea, a zero Bayesian prior probability given your conclusion of no answer. But if a universe has a cause, then the cause must end the chain of causal descent by itself existing without a cause. Doesn't pure mathematics satisfy this? And the other question is by Preston Justice. I've recently read a paper on William Lane Craig's Cosmological Argument, blended with the fine-tuning argument, and know that you had a formal debate with him in 2014. Has your position reasoning changed at all in the past 7 years, and can you please briefly reiterate your counter-argument? So the reason why these two things are grouped together, because at the end of James's question, where he says, if the universe has a cause, that cause must end the chain of causal descent by itself existing without a cause, is very much in line with William Lane Craig's Cosmological Argument. That is part of the cosmological argument, the conclusion being that this cause that exists without a cause is God. So first, to answer James's question, I don't say when we ask the question, why is there something rather than nothing, to say there is no answer except to say the universe just is. What I try to say is that's not an answerable question. That is not a question that has an answer, okay? Just because I can grammatically form a sentence with a question mark at the end doesn't mean it's a sensible question to ask about the universe, right? To ask about reality. When you say, what is the largest prime number? The answer is not a number. The answer is no. There's no such thing as the largest prime number. You shouldn't ask that question, right? Likewise, when you ask why is there something rather than nothing, the question being begged there is it sensible to attach a reason why to the question of something versus nothing? And my answer is no. There's no such thing as the reason why there is something rather than nothing. That's not the same as saying the universe just is, although it is compatible with saying the universe just is. The other thing is, you say that I give Max Tegmark's cosmological views a zero Bayesian prior probability. And so this is pushing a hot button of mine, and let me digress a little bit over this, because a good Bayesian doesn't really give zero prior probability to almost anything, any logically coherent ideas, because you never know when evidence might come along and increase or decrease your credence in those ideas. But very frequently, I will, when asked a question, give an answer to it, right? Like, what is the correct interpretation of quantum mechanics? Well, it's the many worlds interpretation, right? Is there dark matter? Yes, there is dark matter. Is the theory of natural selection basically true? Yes, it basically is. Now, in all of these, of course, what I mean is my credence in those answers is high enough that I'm not going to continually footnote every single claim I make by saying my credence is high, but not precisely one, okay? So for some weird reason, when I talk about ordinary scientific subjects, people seem to get that. When I say dark matter exists, for example, most people understand that what I'm saying is I put a very high credence on the existence of dark matter given the data and information we have and so on and so on. But when it comes to these sort of grand metaphysical / theological questions, anytime I state an opinion, people attribute to me certainty in that opinion. Even though I'm not saying I'm certain in that opinion, I never say I gave zero Bayesian prior probability to anything else. I've never said any words like that. I said, here's what I think is right. That is what I said. So, when I say that, like I just said, for my attitude toward the why is there something rather than nothing problem, probably there is no reason why there is something rather than nothing. I'm not meaning to attribute any certainty to it. And I think it's extremely, one should never assume that just because a person says something that they're certain about it, because it would be very tedious indeed to go through life mentioning your numerical Bayesian credence to every claim that you make, even if that credence is 99%, right? So no one does that, and no one should expect anyone to do that. So it is important to distinguish between making claims, which is always a fine thing to do, and erroneously attaching certainty to those claims. Don't accuse people of attaching certainty to their claims unless they actually literally say that that is what they are doing. Okay, now then we have the bit about, causes and chains of events, and also Preston's question about the Kalam cosmological argument. And, my answer has not changed that much since 2014, which is that the whole talk, the whole discourse of causes and effects is just completely inappropriate in the context of the existence of the universe. The idea of causes and effects, goes back a long time. It probably goes back very, very far, but certainly attempts at formalizing it were made by Aristotle and so forth. But like many ideas in philosophy and science, they start out as informal folk ideas, and then we try to make them rigorous, okay? We try to attach meaning to these everyday human inventions. So we have causes and effects in the everyday world. No question about that, right? The cause of me getting sick was I got a bug, right? And I got sick because of that, because I wasn't wearing my mask. Perfectly sensible set of things to say. But there's no guarantees that that informal notion extends to these huge metaphysical questions that are well outside the realm of our everyday experience. So that was my point when I talked with William Lane Craig, and that will be my answer to your question, James. This whole first premise of the Kalam cosmological argument, everything that begins to exist has a cause. Nope. No, it doesn't. I would respond to that by saying that the notion of having a cause just doesn't apply to things like the universe, okay? What does apply, you might well ask, what applies? Well, I would say that the sensible thing that seemingly applies is, does everything that happens obey the laws of physics? Now, of course, you could always define the laws of physics to include everything that happens. So a better thing to say is there some simple universal set of laws of physics that is working now that allows for the universe, or for all of existence and all of reality, to be self-contained and compatible with that simple set of laws? Now, we don't know what the ultimate laws of physics are, so we can't say the answer to that for sure. But with things like quantum cosmology, the wave function of the universe, etc., we have very good reasons to believe that the universe can exist self-consistently, obeying the laws of physics without any external cause or support or creator or anything like that. So that's the scientific attitude, given what we know about modern physics. Claudio Slamovitz says, I'm wondering if all the fields that make up the universe are present everywhere, or if some fields exist only in limited portions of the universe. A raw definition for field is a physical quantity represented by a number or another tensor that has a value for each point in space and time. Does a particular field still exist in regions of space where the value at each point is zero? What if there are fields whose value is zero at all points? Would we be aware of their existence? So there's two things going on here. One is the first question, would a field exist even if its value is zero? Sure. Because the existence of a field means that it could take on other values. If you invented a field that for some reason could only be zero, that's the only value it could have, then it might as well not exist. The whole point of fields is that they can, in principle, change and interact with other fields. So to answer the second part of your question, would we be aware of it if a field had zero value everywhere? Well, again, it depends on, is it a necessary fact about the field that it always has zero value? In which case, no, we would not be aware of its existence, and it would make no sense to talk about such a field as existing. But if it just happens to have a zero value in some region, but we could bring it into a non-zero value, then we say it exists, even if We don't do that. So it's not just that it exists when it has a non-zero value, but the possibility that we could give it a non-zero value by interacting with other fields, for example, is enough to say that that field exists. Just like the number 0 exists. It doesn't need to be a non-zero number. Peter Solfest says, sorry, I shouldn't have said that last word. That last sentence is gonna make me sound like a Platonist. Things that have a value 0, quantities, right? Like the number of pennies in my pocket. Okay, the number of pennies in my pocket could be 0. It is 0, in fact, right now. But the concept still makes sense. And, we could say that concept exists. The more I'm saying this, the more it's a bad analogy. Fields are special. Fields having 0 value have no trouble at all. Here's a better analogy. The temperature is 0 in degrees Celsius, okay? That doesn't mean that there's no such thing as temperature. It just means the value is 0. All right, Peter Solfest says, when working through a new idea or cranking through math, what's your preferred working medium? Whiteboard, chalkboard, tablet paper, etc., and why? So I generally go back and forth between 3 media. Like in many ways, when people ask about my work habits, I just don't have a very systematic procedure. Sorry about that. But there's something nice about working standing up at a blackboard or whiteboard. Unlike many of my colleagues, I am not all that invested in whether the board is black or white, okay? I like whiteboards just as much as blackboards. A lot of people have a sort of aesthetic preference for blackboards. I get it, but that's not me. I just don't care. But there is something nice about standing up, and also you can sort of see things in front of you, and you can sort of erase and shape things, and that's very nice. But the problem is you can't be very detailed about it, right? Like you can't fit that much onto a blackboard. So at some point you got to sit down and write. And traditionally, I've done that with pen and paper, but mostly these days I've switched over to iPad and Apple Pencil, okay? The same sort of technology that I use to do the Biggest Ideas in the Universe series is what I do to take my notes. There's pluses and minuses there. The huge minus is you can't, set out 20 pages in front of you and look at them all at the same time. And the access time to different pages is actually slower on a tablet than it is in person. On the other hand, there's a huge benefit, which is that you can cut and paste. That is a huge benefit. The other huge benefit is that I'm walking around with my iPad. I have every note I've ever taken since I got the iPad. Whereas other notes that I do on paper, I tend to put in a file and then never take out of the file ever again. So I think that overall, the tablet is winning a little bit. But, I'm open to that changing down the road. And then finally, since usually these ideas that I'm working on are in the context of some hopefully deliverable product, like a paper or a book or whatever, I'm also typing at the computer. So I'm very often, I have a fodder file on my computer where there's a list of ideas that I someday want to write into papers or books. And when one of them grows up to be more than just a paragraph, it will get its own file in a folder on the computer, and I'll type in ideas that will eventually become an outline and hopefully eventually a paper. That's how it works. So back and forth between some text files on the computer, the tablet where I can write and do other things, and then the blackboard where you can sort of conceptualize everything and also talk to other people. The social aspect is very important. Joseph Williams says, did you expect LIGO to detect the gravitational waves propagate at the speed of light? Do we fully understand why that is? So yes, I expected that, and yes, we fully understand it. It's because gravitational waves are massless. We understand it mathematically. You can, in fact, if you buy my general relativity book, you will prove it for yourself. The wave equation in classical general relativity looks basically the same as the wave equation for Maxwell's electromagnetism. So remember that there's nothing special about the speed of light. There's something special about that speed. The thing that is special about it is not that light moves at that speed. There is a special speed built into the fabric of space-time. The speed at which you can't ever travel, the limiting speed if you are a massive particle or object. It's the relative velocity between two particles that are both massive can never be as large as a certain speed, It just so happens that light travels at that speed. And you can see that from the particle point of view by saying the particles are massless, or from the wave point of view by just looking at the equation that the waves obey. And the equation that gravitational waves obey is basically the same as the equation that light waves obey, electromagnetic waves obey. When I say basically, it can't be exactly the same because light is a spin 1 wave and gravity is a spin 2 wave, so different tensor structures. But the differential equation that tells you how the wave changes from moment to moment in time and in space, those are exactly the same structure for light and for gravity. So that is exactly what you would expect before you ever turned on LIGO, and it's exactly what we saw. To change that, to give either light or gravity some other speed is actually very challenging, given what we already know about those two phenomena. So people sometimes try to do it, but it's very tricky. Phil Moyer says, I'm still not clear on the relationship between space-time curvature, e.g. de Sitter versus anti-de Sitter space, and the cosmological constant. First, how does the cosmological constant show what kind of space we live in? Second, what does current research tell us about the curvature of our space? Good. So there's a couple things going on here. One is, I mentioned before, but I'll say again, there's a difference between the curvature of space and the curvature of space-time. So the curvature of space-time makes perfect sense. It's something that we can define. The curvature of space implicitly means, if you're even going to talk about that you've divided space-time up into space and time, right? So you can assign space a curvature. Now, in both cases, space and space-time, if you're completely careful about it, you need tensors to characterize the mathematical structure of that curvature. In other words, it's not just a single number. It's a set of numbers that answer a bunch of questions about how the curvature of space is affecting particles moving in different directions, or something, some equivalent physical notion. But we very, very often simplify. Okay, so we consider spaces or space-times that we call spaces of constant curvature that is the same in every direction and the same at every point. And there you go by making that simplification from an infinite number of possible curvatures, different ways that the space or space-time can be curved, to a very small number, namely 3. Either space or space-time, if it's uniform, if it's constant curvature, can either be zero curvature, positively curved, or negatively curved. Okay, so when you're talking about this particular distinction, de Sitter versus anti-de Sitter, usually we're talking about, that means talking about the curvature of space-time, not about the curvature of space. And I mention this because if in the real world, we don't live in either de Sitter or anti-de Sitter, because de Sitter and anti-de Sitter are solutions to general relativity with zero matter in them. And by matter, I mean any propagating form of energy, including radiation or fluids or whatever. They're empty universes. They are vacuum solutions to Einstein's equation of general relativity. The only non-zero source that you include to get those solutions is the vacuum energy, the cosmological constant. So basically, if you have no matter, no energy other than the vacuum energy, then if the cosmological constant is positive, you get a de Sitter solution with positive curvature. If the vacuum energy is negative, you get an anti-de Sitter solution with negative curvature. And if it's zero, you get a Minkowski solution with zero curvature. And roughly, those correspond to test particles moving together over time as a positive curvature, as like you're on a sphere, or they could move apart over time with negative curvature, or you can have zero curvature like Euclid thought about, but the space-time version of that. And as you know, Euclid thinks that initially parallel lines remain parallel forever. Same thing is true in space-time, in Minkowski space, okay? So in that case, it's a very simple, straightforward relationship. There's nothing in the world other than the vacuum energy tells you which space you're in. But as I started to say a minute ago, we don't live in the vacuum. You and I are not made of the vacuum. We're made of particles, okay? So we will asymptotically approach the vacuum. The universe is emptying out, coming closer and closer to the vacuum. And the fact that we think the cosmological constant is positive means that we're approaching de Sitter space. But right now, we're not in de Sitter space. We're in something that is approximately a homogeneous and isotropic cosmological spacetime. So if you look at the distribution of galaxies or radiation or anything like that on very large scales, it is approximately uniform. That lets us pick out a preferred way of dividing space-time into space and time. And then we can talk about the curvature of space all by itself. And we can say, is space positively curved, negatively curved, or zero? And the important thing is, there's a very long-winded way of getting at a single important point. The curvature of space is completely independent from the curvature of space-time. You can have, let's say, a positive cosmological constant, so that you will eventually approach de Sitter space in a positively curved universe. And yet, in the time period, in the era where you still have matter and energy other than the cosmological constant, your spatial slices of space-time may very well be either positively curved or negatively curved or have zero curvature at all. And in fact, in some cases, there's more than one way of slicing space-time. If you were actually in de Sitter space, if there was no matter, if you were in a vacuum solution where you had de Sitter space-time, you could equally well slice it so that spatial slices were completely flat or that spatial slices were positively curved. So it's a complicated relationship overall. So just keep your wits about you and make sure you know whether people are talking about the curvature of space or the curvature of space-time. Nicholas Walker says, priority question. Remember, priority questions are, you're allowed once in your life to ask a question that I will try to answer. And I can't answer every question because there's too many questions, but I will always try to answer your priority questions. But you only get one, so make it a good one. And Nicholas says, I recently watched a program that said that our current best view on gravity is that it emerges from some description of the universe that has no space and time in it at all. In information returned to the universe from black holes imprinted in radiation. Could you help explain this? How much of an explanation do you need? We did a whole episode with Netta Engelhardt on this kind of problem, on the black hole information problem. So I'd recommend you check that out if you haven't already. But there's a couple of ideas that maybe got smushed together here a little bit. There's the idea that the fundamental description of space-time as you and I know it is fundamentally quantum mechanical and doesn't start with space or time at all. Or maybe it starts with time but not space, maybe even space but not time. Like, all these options are on the table. Something that is crucially important to emphasize here is that we don't know, right? I mean, the state of our current knowledge here, it's all very, very speculative when it comes to these things. So keep an open mind about what the possibilities are. But the point is that if you take quantum mechanics seriously, the universe is a wave function. And the wave function has its own status, its own existence as a vector in some giant Hilbert space, as we were talking about earlier. And so you want to be able to describe space and time, or at the very least space, as well as all the fields and particles, etc., that we're made out of, as emerging from that underlying Hilbert space, vector in Hilbert space way of thinking about things. Now, that's a very sensible program to follow, and I'm very, very interested in that. I've written about it. My most recent paper is literally called Reality as a Vector in Hilbert Space, so you can check that out, or my most recent paper on this topic anyway. Now, the implementation of that, how does space-time really emerge from this abstract notion? That's a tricky thing, and that we know even less about. And so when you say, in information returned to the universe from black holes imprinted in radiation, well, maybe, but certainly not necessarily, right? Like, most information of the universe was never in a black hole, was never returned to a universe, anything like that. Those sets of words appear in a context where you have put some information in a black hole, you've made a black hole, some quantum information has fallen into it, and you're asking how it comes back out. And crucial, if it does come out at all, which many of us think it does, there seems to be a crucial step in which you're not attributing anything like a location in space to that information. The information is somehow spread out in a non-local way. And the details there are remaining to be worked out. I wouldn't want to make you think that it was almost all set. So that's the motivation, the philosophy behind it. But, we don't completely understand it quite yet. So that's all I'd be willing to explain right now. Ben Stein says, based on your interview with Edward Slingerland and your discussion of Taoism and Confucianism in the context of modern neuroscience, do you think these two ancient philosophies might actually be more similar and interrelated than they seem? In other words, might Confucianism's call for self-cultivation neurologically develop into the action without intention of Taoism? Put another way, as was hinted on your show, is intense practice of the piano and study of physics usually necessary for musical improvisation and physical intuition? Yeah, honestly, I'm not the one to ask about this, so probably I shouldn't even have tried to answer it, but I don't want to speak for Taoism and Confucianism. I'm not an expert on those things, so I have to disappoint you on that. But the reason why I wanted to answer it was because, there is a sort of hopeful tendency, or a tendency to be hopeful maybe, when you think about competing philosophies, whether they're religions or more secular ways of thinking about the world, to say, like, aren't they all one at heart? And I think that the general answer, even though I don't know enough about Taoism and Confucianism to say, but I think that the general answer is no, right? Like if we were talking about consequentialism versus deontology versus virtue ethics in the realm of ethical and moral philosophy, I think they're really different. And I think that, not all religions are really the same. I think that Confucianism has an emphasis more on the social aspects, on working within a society in a successful way, playing your role, taking up your place in the hierarchy and fulfilling the requirements and the intentions of being in that place. Whereas Taoism is more individual, right? It's more about cultivating yourself for intrinsically virtuous reasons. And so, again, even though I'm not an expert enough to say with any definitiveness, I don't necessarily think that they were sort of going along the same path. They can be compatible in many ways. Like I can certainly imagine that being your best individual self is completely compatible with playing your best role in a society. But that's what I don't really have enough knowledge about to say whether or not they really are compatible. A real expert would actually know. Bachi A says, would you mind describing your writing process? Once you've settled on an idea for a book, do you follow any particular system that guides you through completing it? So like I just hinted at, my process, such as it is, kind of chaotic, kind of non-systematic, I guess would be a better way of saying it. I know that there's a very popular genre out there, right, of what your writing process should be, kind of a self-help genre, or what the great people did, and maybe you can be inspired by that. But I think that everyone's different, and I think that people should be different, and their processes should be different. I mean, my wife Jennifer is a writer; she writes more than I do, and our processes are utterly different, even though they both come to a successful conclusion, I think, in very different ways. So anyway, all of that is preliminary to saying I might have my process, but it shouldn't be your process. As to what my process actually is, it's unlike other people, I do as much thinking and outlining as I can, and reading and research and sort of conceptualizing in my brain before I write anything. So a lot of people will, write a lot of rough drafts and, just core dumps, free writing, get something on the page, then eliminate a lot of it, cut and paste it, blah, 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 blah. That is not my process. I really try to think in the most organized way possible about what I want to say, where I'm going, and then once it comes to actually writing it. So the downside of that is a lot of my working habits look like I'm not doing anything at all. I'm just sitting there. But then the good part of it is that once I actually get to writing, I don't need to revise very much because I really have a pretty clear idea of what's going on. And when it does actually come to writing, like I will typically signpost. So like I'll write a very brief outline, right? And then I'll just go back and fill in the outline with the words I want to say. And like going along with this philosophy is, the idea that I write from the start to the beginning. Like I can't imagine writing chapter 7 before I've written chapter 6 of whatever it is I'm writing, because I have the whole outline in mind. I generally have a title in mind, even if it doesn't end up being the title. But like a person who can write a book and not know what the title is going to be, that's very alien to my way of thinking. Let's put it that way. So very encouraging to people to do it other ways. But, I have this method where the whole thing is basically in my head before I start. DLP says, what is your favorite standalone science fiction movie of the past 10 years? Standalone meaning not part of a series or set in a larger fictional universe. So I don't really have one, and I almost didn't answer this question for that reason. I thought I didn't have anything insightful to say. But then I was thinking about, maybe, I just don't really keep in my head a list of top 10 movies or whatever, right? So maybe there was some movie the past 10 years that I just have forgotten was really great. And so I actually, went back, inspired by this question. I looked up, what were the great science fiction movies of the past 10 years? And part of me thinks that I'm not that impressed with any of them in the past 10 years. Some of them are very, very good. There's a lot of great movies out there. I really liked, Looper, The Martian, Ex Machina, Gravity in a slightly different way. I will confess that I didn't watch Arrival, which everyone says is really good, so I should have to do that at some point in time. But, all of these are, in my mind, pretty good, but not like super great. They weren't indelibly stamped into my consciousness like a really great movie would be, or even super duper memorable so that when someone mentions them, I go, oh yes, let's watch that one again, right? I think they're pretty good. Yeah, and maybe it depends on exactly how the question was asked. So 10 years is a certain criterion. If we included Eternal Sunshine of the Spotless Mind, that's outside the 10-year window. But that, I would say, was a truly great movie that impacted me quite a bit. If we included Get Out as a science fiction movie, which arguably you could do, it's closer to horror, I suppose. That, I think, was a truly great movie. But yeah, so for example, but I guess what I'm getting at is, the point of me answering this question is, I don't know if it's my fault or the movie's fault that I don't have a real favorite here. It's certainly plausible to me that it's my fault, right? That there is an era of your life when you're in your teens or your 20s maybe where you're more impressionable. So you see a movie and it just has a big impact on your life. And then when you reach a certain age, as I now have, it's just harder to see a movie and say, ooh, that was really a life-changing experience, right? But a movie doesn't need to be a life-changing experience to be good. So I'm not sure that it is my fault, to be honest. So think, for example, about Looper, directed by Rian Johnson, which I really liked, but he also directed Knives Out, which I loved. I think that Knives Out was a way more impressive movie than Looper. And Looper was good, but Knives Out was better. Like, Knives Out was one of my favorite movies. And why? Like, is it just, sometimes one movie is better than another? I kind of wonder, this question is making me wonder whether science fiction on screen, or at least on the movie part of things, is in a lull these days. Obviously, science fiction commercially is hugely successful, and DLP very specifically said don't include larger fictional universes, but we know there's some very successful large fictional universes out there. But I'm thinking about these movies, and there is a certain, well-troddenness to them in some sense. Like, we know the moves, we know the scenarios. There's some individual surprises, but, okay, we've seen The Matrix. We've seen time travel movies, and it's a little bit less truly new and deep in some way. So, Looper was a time travel movie that was very well done, very competent, it was fun and it was good as a movie. But the science fiction didn't really, blow my brains away. And Knives Out wasn't trying to be a movie that blew my brains away, right? It was just a mystery story with some kooky characters in it, but it was just so good at being that I thought it was much more successful as a movie. Maybe the science fiction on screen these days is sort of less grandiose, less important, less significant in some way. Or maybe it's just that the really great people are mostly doing TV these days. That's completely possible, right? I mean, maybe the brilliant screenwriters are doing things like Black Mirror and The Expanse, and who knows, Foundation might be there at some point. We don't know. Game of Thrones, if you want to include fantasy as well. So I don't know. So this question made me think more than I expected it to. And I don't think I'm missing any great movies. And of course, everyone's feeling about movies is going to be different. So I'm sure that everyone has very different opinions about this than I do. Emmett Francis says, what defines something as a branch of physics? Your conversation with Nigel Goldenfeld helped me think through this a bit. Part of it seems to be just that the same sorts of models, like the Ising model, that apply to basic physical systems also work quite well when describing higher level systems. So is it just that mathematical models and tools happen to carry over to other fields? Or is there something deeper that defines something as physics versus quantitative modeling? So I thought, I guess I got confused by this question because I thought when you asked what defines something as a branch of physics, that we were contrasting physics with, chemistry or geology or biology or whatever. But then at the end, which is an intrinsically interesting question, right? I mean, with Nigel's conversation, showed us how to use techniques that you develop by being a theoretical physicist and put them to work in studying biology, either molecular biology or evolutionary biology, etc. So the boundaries are fuzzy in that sense, and maybe that's perfectly fine. I don't really care whether we call it physics or not. But then at the end, Emmett puts in this thing where he says, is there something deeper that defines something as physics versus just quantitative modeling? I don't know what that means. So it's not physics versus other subfields of science, but physics versus quantitative modeling. Modeling is a part of physics, I guess. Quantitative modeling is a part of physics. Part of the scientific method broadly is inventing hypotheses, which you could call models, and then figuring out what the predictions are of those models, comparing them to the data, and so on and so on. So I got confused at the last bit of that question, physics versus quantitative modeling. The physics versus biology and chemistry question, part of my answer would be, who cares? Don't try to reify these artificial boundaries. Just do good science and learn about the world. But there is sort of a human scale question. Why do we tend to think of some things as physics and other things as not? Your first impression or your first guess is, well, we think of simple systems as being physics. And once they become complicated, they become something else, right? Chemistry or biology or whatever. But complex systems or complex behavior can arise from very simple physical systems. That's the whole point of what Nigel was talking about. So it's not a very cut and dried criterion. And honestly, if I think about it, I'm not quite sure that there is a cut and dried criterion for saying that something is physics versus some other way of doing science or other subfield of science. Rebecca Lashua says, Bostonian here, what are some of the things you like to do when you're in town? How do you like it here in general, and how would you compare it to LA? So other than the weather, we'll not talk about the weather. Like I said, I lived here 8 years, 5 in grad school and then 3 in postdoctoral years. So I know the weather very well, but it's a shock to actually go through it. But I love Boston. Boston is a great city, and I'm a city person in general. I think most cities are great. Like once you have a critical mass of things going on, I'm pretty successful at finding things that entertain me. Right now, I'm sort of in the downtown crossing Chinatown area, so there are more dumpling houses and hot pot restaurants around me that I can possibly sample in a finite period of time. But that's fun. I'm going to try. Overall, the food scene in Boston is not that great, to be honest, compared to cities like LA or New York or San Francisco or Chicago. But Boston obviously has a lot going for it. The single best thing, look, I know I'm biased. Okay, I'm very, very biased. I'm not everybody. But if I were a Bostonian, the thing I'd be most proud of is that it's the best university town around, right? And we're including Cambridge. And for that matter, let's include Medford. So Tufts can get in there. But Harvard and MIT, obviously, but also BU and BC and Tufts and Northeastern and a whole bunch of places. Brandeis, even, let's include that. The amount of smart people devoting their lives to intellectual pursuits is just amazing here in the Boston area. That's my favorite thing. And, it's not very original or anything like that, but if I'm being honest, that's what I like about it. What do I like to do? I don't think that the things I like to do in Boston otherwise are that different than other places. Eating, drinking, going to music, things like that. But I'm not doing a lot of those things because, number one, I'm by myself. Jennifer is still back in Los Angeles. And number two, there's a pandemic. So I'm not like hanging out in clubs, going to hear music or anything like that. Hopefully, I'll be able to come back under better circumstances pretty soon. How would you compare it to LA? I mean, it's very, very different. That's the interesting thing. Even though they're both cities with an amazing number of things to do, they're very different. And and in many of the ways, I would give Boston the edge in some ways because it's more walkable, right, or more public transportationable. And that sounds trivial. It's just a way to get around rather than what you do when you get there. But it has an impact on how you interact with the city because in LA, because you have to drive everywhere, it's hard to find things in LA. You can't just like here in downtown Boston, I can walk in some direction and interesting things will appear. Or if I'm walking to some place for some particular reason, I will notice interesting things that I hadn't anticipated before, right? Places or, stores or whatever. Whereas in LA, you better know where you're going to find anything interesting. You better go there, and then wandering around the neighborhood is usually less rewarding in a place like LA. There's some specific neighborhoods that work quite well in Hollywood or whatever, Santa Monica, but it's harder in LA. I think LA is wonderful. The fact that the entertainment industry is centered there is a wonderful fact about LA. The weather is pretty nice. I said I wouldn't mention that, but I really, really like LA. But I like Boston too, which is why it's fun to spend a couple months here. Ken Wolf says, are you familiar with Eric Drexler's publications on his ideas for what sort of capabilities molecular nanotechnology could eventually bring about? So, I had Eric Drexler's book years ago. He wrote a book, Engines of Creation, one of the very early nanotechnology books. I don't remember reading it, so I cannot specifically answer that I know what was in those books. But I wanted to answer the question because two things. One is that, and I think I've said these before, apologies for people who have heard me say it before, tiny, tiny, tiny technologies are going to be hugely important in the near middle term future. I think we underestimate how important they're going to be. Nanoscale technologies in general are going to have an enormous impact on human lives. But I had this vague feeling that the biggest impacts are not going to come from what we traditionally think of as nanotechnology, but from what we traditionally think of as synthetic biology. As Francis Arnold put it, the Nobel Prize winner, a lot of good engineering at the nanoscale has already been done by nature. And we can use the ideas that nature has come up with and modify them for our own purposes. But that's going to be a much quicker route to world-changing technologies than just to build little machines directly ourselves. And in fact, we've seen this, right? We've seen this with CRISPR, which we had a podcast episodes on with Fyodor Urnov, where CRISPR is something that exists in nature. Bacteria invented it, and we are just repurposing it to edit genomes for ourselves. So I think that the picture that you might have in mind of like little tiny machines, where machines are literally made of metal, they look like little tiny miniaturized versions of robots, is probably not the right one. The world at that scale of being really tiny is just a different world than our macro scale, and the appropriate way to be and way to survive and way to thrive is probably to look more like a cell than look like a little robot. So nanotechnology will be important if that includes sort of cellular biology, synthetic biology, things like that. Madeline Carr asks a priority question. Do you think the concept of Bergsonian duration, the experience of lived time through the immediate data of consciousness, will ever be reconciled with scientific clock time, and by what approach? Yes, I do. I think there's something missing here that I'm not getting in the question. So sorry that it's a priority question. I'm going to give you a disappointing answer, but the approach is by doing neuroscience and psychology, I guess, right? I see no tension between the experience of lived time through consciousness and scientific clock time. There's like almost no barrier to answering that question. I mean, our brains are made of little things that obey the laws of physics, the laws of chemistry, the laws of biology, and they tick along like little clocks, and they have rates of doing things, and it takes a certain amount of time to do different things. And the collective behavior of all those little pieces gives us consciousness and gives us the experience of living through consciousness, and that is responsible for our experience of time. So I don't, I mean, of course, all the details are not yet worked out and will take effort to work out. And I'm not going to predict when they're going to be worked out. But it's not something where there's a huge paradox or puzzle that we see no way of resolving. I think it seems like it's clear how it will eventually be figured out. Luke DiGiacomo says, priority question. I am 25 years old and a software developer, a great job I like well enough, yet I want so badly to be able to learn and work on the foundations of quantum mechanics. If I were to decide to make that jump, where would I need to begin? So thanks for asking the question, but I'll answer it not just specifically for you, but in more general. We live in a world where this is easier than ever has been before to go from no knowledge of professional physics to expert level knowledge of it, because we've always had books, but now we have online courses, lecture notes, online talks, and things like that. So if you wanted to do something like this, I'm not saying it's easy or even doable, but it's more doable than it used to be. Really what you need two things. You need a curriculum. So you need like a list of subjects to learn, and then you need the actual motivation to do it. I mean, it's very, very easy to say, I'm going to learn all these things. It's much, much harder to do it. It's like saying, I'm going to lose 10 pounds. That's very easy to say, harder to do for many people in actual fact, because it takes a long time to actually hold yourself to that standard. So you can find curricula online. I always point people to Gerard Etouffe's website. Etouffet is a brilliant living physicist, Nobel Prize winner, and he has a website which is called something like How to Be a Good Theorist. And he gives a very detailed curriculum that you can go through and learn, and he links to online lecture notes as well as textbooks and things like that. So you could just do that. It would take you a long time, but there's no royal road to geometry. It takes time. The only problem with Etouffe's list is that there's too much in it. Like, he's a genius and a brilliant guy, and he's giving you an overwhelming amount of stuff you need to learn. And so I've often contemplated making a companion webpage saying, instead of how to be a good theorist, like how to be an adequate theorist, where it was sort of the minimal set of things you need to know. I mean, you need to know calculus. But how far back do you go is the question. You clearly need to know algebra, okay? Algebra, geometry, the basics, trigonometry, calculus. And then beyond that, you need to know differential equations, vector calculus, complex analysis, various techniques within mathematical physics to solve differential equations like series expansions and transforms, Fourier transforms especially, a little bit of matrix mechanics, linear algebra, right? And that's the basic mathematical toolkit. And then with those, you learn the traditional curriculum is classical mechanics, electromagnetism, quantum mechanics, statistical mechanics and thermodynamics, and then options after that. But it doesn't sound like too much, right? Classical mechanics, quantum mechanics, electromagnetism, statistical mechanics, and thermodynamics. And the options include general relativity or nuclear physics or particle physics or cosmology or astrophysics or biophysics or many, many different things. But all those topics are available online if you really wanted to do them. So I don't know what your starting point is, start with classical mechanics. Buy a big textbook, or find a textbook online, Physics 101. Start reading it. See how far you get. Suraj Rajan says, priority question. Is there a physical distance that two worlds in the many worlds interpretation have to maintain to stay distinct? More generally, can the many worlds occupy the same classical physical space? So, nope. I have to undo the question, in fact. There's no such thing as physical distance between many worlds. So it's not that there's a certain physical distance they are separated by to become different worlds. There is literally no such concept as the distance between the worlds. It's the other way around. Space lives within each world separately. It's not that the worlds live within space, okay? And this is a difficult little mental jujitsu to wrap your brain around because we're not used to thinking that way. We used to think about things living in space. But in quantum mechanics and the many worlds interpretation, the thing that matters is the wave function of the universe. And that's not in space at all. Space is in it. And for each different world, there's a different copy of space There's no distance between them because there's no space in between the different worlds. Crather Lucas says, is there more than a semantic difference between saying our universe splits and branches, thereby creating more universes, and saying that all the universes in many worlds already exist but differentiate over time? So I think that there is a difference. But, many people have asked this question. I never actually myself have thought about it very, very carefully. So I'll give you my tentative belief answer. But again, subject to updating if someone explains it to me better. What do you mean to say different worlds? There needs to be some meaning to that statement, right? When are two different subsets of some big physical structure different worlds? So I think that the answer is that if you change the physical situation in one of those worlds, the other world doesn't notice, right? It will never notice, as long as it goes on. There's no difference in the evolution of one world if you start from a different starting point in the first world, okay? That's the nature of things in the many worlds interpretation. If you have a branching event, so now you have two different branches of the wave function, and I imagine, again, hypothetically, doesn't happen, but hypothetically, counterfactually, putting my finger in there and messing with the physical situation in one of those worlds, what happens in the other one? And the answer is nothing. There's no observable effect. Very, very similar, but different, different conceptually, but similar conclusion to the cosmological multiverse, where the different universes, as we call them, are literally just so far away that nothing that happens in one universe can affect the other. As we just discussed, here in many worlds, there's no distance between them, but they are causally separated. So if you want to say, well, maybe all the worlds were always there, but we just didn't differentiate between them, I don't think that's right. Because if you went in and poked one of those purported worlds before the branching event happened, before decoherence happened, that would be noticeable in the other parts of the wave function. So again, I'm not 100% sure that's the best way of thinking about it, but that's how I think about it right now. So open to modification if someone gives it to me. Max Plan says, a while back, I think you organized a series on naturalism called Moving Naturalism Forward. I love those discussions and learned a lot from them. Have you ever thought of organizing something like that again? So yeah, for those of you who don't know, back in, I think, 2012, I helped organize, well, I did organize, it was mostly me, it was one workshop called Moving Naturalism Forward. You can find it online. All of the videos are there. It's a wonderful thing. We just got a bunch of people in a room, and for 3 days we talked. It was cut short a little bit, more like 2 days, because there was a giant hurricane that hit Massachusetts where we were, so people had to run away quickly. But it was, philosophers and physicists and biologists and neuroscientists all talking to each other. Richard Dawkins was there. Steven Weinberg was there, Dan Dennett was there, as well as a bunch of former Mindscape guests. Jan Levin was there, Alex Rosenberg was there, a bunch of other people. And we had a great time. The whole point of it, the motivation of this was so much effort had been spent in the atheist/naturalist community in saying that God didn't exist or saying that religion was bad or something like that, right? A huge amount of effort. And fine, it's true. I agree that God doesn't exist. But okay, what are you going to do about it? How are you going to live your life now that God does not exist? Like Nietzsche has asked us this question, and have we given a completely adequate answer to it? And I think the answer is no, we've not given a completely adequate answer to it. And part of the evidence is from that workshop. If you look at the discussions, we didn't agree with each other on a bunch of things, okay? So there's plenty of work. Once you say God doesn't exist, you're not finished. So that's why we called it Moving Naturalism Forward. So let's agree, zero time was spent arguing about the existence of God. We all agreed that God didn't exist, but okay, what's the meaning of life? Do we have free will? How should we be moral, right? These are the questions that we addressed. Simon DeDeo, David Purple, other Mindscape guests who were on there. I'm sorry that I'm forgetting people. But anyway, I think it was very, very productive. It was very interesting to hear people. And it was also productive because there was almost no agenda, right? Like I sketched out an agenda, like if it's this morning, then we're talking about the meaning of life. And I designated one person to lead the discussion, and we just discussed. And it was a small enough group that we could do that. And, it worked, I thought, beautifully. And we never, we didn't say we're going to write a book or anything like that. There was no obligations. So it made people willing to go. And so it was very useful. Am I going to do it again? Maybe. I don't know. I don't have any current plans. It is work setting these things up, So I only have a finite amount of time in the day. So I have to choose what I'm doing. David Wallace and I have actually thought about moving Everett forward, doing a workshop with just a few people who are all Everettians, because, there's lots of workshops on the foundations of quantum mechanics, but we're constantly arguing over what is the right theory of quantum mechanics. And there's sort of intra-Everettian questions to be asked, which are very, very interesting. And so maybe we could do that. And, this is not to say someone else couldn't have a theory on moving cubism forward or moving pilot wave theories forward. Good for them. They shouldn't be bothered by talking to Everettians all the time. They should be able to talk to themselves too. And I'm sure there's a million other things. So I will certainly be organizing workshops going forward, but I'm just not sure which ones. Tim Kennedy says, near the very end of a recent AMA, you spoke about how you were leaning away from consequentialism and more towards deontologism. Could you share more thoughts about that? So I'm not sure if it's toward deontologism or not, but it's certainly true that over the past 10 years or so, maybe that's a little bit too many years, but I guess since writing The Big Picture, which was more like 5 years ago, when I really needed to sit down and actually put onto paper some of my ideas about ethics and meta-ethics. I had already become a little bit skeptical of utilitarianism and consequentialism, which was sort of my natural, comfortable home in my early days, thinking about morality and so forth. It's very, very compatible with being a scientist, right? As we will talk about on a very soon upcoming podcast, there is a seductiveness to quantitative measures of things and clarity, being able to say this is bigger than that. And that's a wonderful feature of consequentialism and utilitarianism. There's a number, utility, and you add it up and you maximize it. What is better than that? Whereas deontology is the idea that, rather than just maximizing some consequences of your actions, you follow rules, okay? And I need to keep including, which I didn't do very well in The Big Picture, but there's another approach called virtue ethics, where rather than following rules, there are some virtues you aspire to, being brave and loyal and helpful and kind or whatever they are. And it's more the aspiring to these qualities than the following of these rules that is important. And so I think that consequentialism is a natural guess, a natural intuitive starting point for trying to be a moral person, but I just don't think it works. I don't think there is a number called utility that you can add up and maximize. I am certainly a constructivist about morality. I don't think more objective morality is out there in the universe to be found. I think that we construct our moral theories. And so the question is what to construct and on what basis do we pick some moral principles over others? And I think that that's sort of a kind of an agglomeration of some combination of our intuitions that we're just either born with or we develop over biological time, and our teaching or learning, I should say, our experience in the world, gives us some impressions. And then, of course, our intellect, our cognition is able to try to systematize all of these inchoate initial starting points. And I think that if you admit that morality is not objective. Sorry, let me back up because this is an important point and I should try to get it right. Think of someone like Peter Singer, the world's most famous utilitarian, okay? Recent winner, I combined two words there, winner of the Bergsonian Prize for philosophy, $1 million prize. And very, very influential in thinking about animal rights and other issues in the philosophical world. So he comes to some conclusions that most people think are counterintuitive, especially about the rights of disabled people and mentally handicapped people and things like that. He thinks that the world would be better off if we were I don't want to put words into his mouth, and I'm sure I'm not going to get it right. Let's just say he is much more willing to contemplate ending the lives of people who suffer than many other people are, because many other people have deontological intuitions where ending lives is bad, and Peter Singer is a thoroughbred consequentialist. So he says, well, if they're suffering, then it'd be better off for them not to be here. And to me, this is an example of you start with some moral intuitions, like increasing utility and happiness is good. And then you develop a theory on the basis of that, like I'll be a utilitarian. But then you reach a conclusion that is incompatible with your initial intuitions. And there's a point of view that says, well, so what? You know, I've reached a conclusion and I believe my theory. So even though my theory contradicts my original intentions, I should believe the theory if I'm going to be logically consistent and intellectually coherent, right? And that's an attitude. That's Peter Singer's attitude. My attitude is, if the theory leads us to conclusions that are incompatible with the premises on which we built the theory, that just means the theory is bad and we need a better theory. And I think that utilitarianism or consequentialism always does that. It leads you to these conclusions that are incompatible with the initial intuitions that you were using to construct your moral theory. So I'm not sure what exact replacement I would advocate for consequentialism, but some version of deontology and or virtue ethics is more like it. Roughly speaking, I mean, becoming more fuzzy about morality. I'm becoming less and less convinced that there is a clear, crisp set of rules or principles we can write down. And I think that's compatible with the idea that we're constructivists. You know, the basis, the starting points for our construction of morality are themselves unclear, ill-defined, imprecise. So to attribute perfect clarity and precision to the outcome is probably a mistake in some way. I'm not sure I want to defend that 100%, but that is roughly, tentatively the direction in which I'm moving. Josh Hedgepeth says, in a cosmos with infinite worlds where all points in time are equally real, how does one reach a sense of self? Are our past and future selves, or future selves, any more us than our parallel counterparts? So yeah, this is part of the important and weird issue of personal identity in the many worlds interpretation, where there are parallel worlds with copies of us in them. And I think you need to update your sense of self to make sense of many worlds. In a single world cosmology where things only happen once and we all agree what those things are, and they're all sort of continuous in space and time, then it makes sense to talk about the life of an individual person as constituting a coherent self, right? You're born, you age, you experience some things, eventually you die. That makes sense because we all have that same set of shared experiences. We know what it means, etc. It would be complicated if someone builds a transporter machine. We'll talk about that later. If you could copy yourself and appear somewhere else, and the old copy of you was still there, now there's two of you, well, then the sense of self would be different because you're faced with a different set of circumstances than we ordinarily are in our experience of the world. Likewise, if you believe in many worlds, then the reality is different than our experience, so we have to update our notion of what we mean by a single set of selves. So I think the sensible way to do it is to think of each person on each world as having a self. And the wrinkle, the complication, is that if you have multiple people on different worlds who came from a single past self, then they share a universal past, a common past, but they don't share a common future. The things that will happen to them in the future are distinct. So that change, the fact that they do not share a common future, to me means they're separate people. Okay, that would certainly be the case if you made a duplicate of yourself and the duplicate was very far away and the duplicate was living their own life and they were experiencing their own stuff completely different than what you were experiencing. There's no sense whatsoever in which that's also you or the same as you or part of one collective you, right? Even though you share the same past, your futures are completely different. That's the situation in many worlds. Happily, in many worlds, unlike the duplicator machine, we're never going to see those other people. So it just doesn't at all matter, right? I would advocate that each one of them is a separate self, but it also doesn't matter. As long as you don't sort of try to group yourself into some collective being, the fact that more copies of you will split off and live in different universes is irrelevant. You personally, any one of those individual copies, can think of themselves as having a unique past and a unique future. It's true about the unique past. The future, it's not true, but for all intents and purposes, it is. So I think that even though you need to change the words around a little bit, the actual operation of the sense of self isn't any different in many worlds than it usually would be in a single world cosmology. Marian Marcali says, I was listening to the latest Complexity podcast with Brian Arthur on economics. By the way, I should say, you mean the latest podcast episode of Mindscape, but there is a whole podcast called the Complexity Podcast, put out by the Santa Fe Institute, which you might be interested in checking out. Okay, question continues. Basically, the theory is so abstract and divorced from the world, and this makes it very successful in some aspects, but too disconnected and unable to actually model reality correctly. It should be a more complete dynamical process, more algorithmic, computational in nature. It seems maybe mathematics and physics are in the same situation, with many disconnected fields or tools or theories, but not a central core. Is this way of thinking applicable to physics? Maybe hypergraphs are the underlying topology for the QFT equations or something like that. So I'll put aside whether I quite agree with your way of talking about what Brian said vis-a-vis economics. I mean, economics is the theory, the standard theory of economics as it currently exists is successful at some things, less successful in others, and it's complicated to draw the line between them. But for physics, I would say the answer is no. This is not a good analogy, or it's not the same situation anyway. Physics has shared underlying theories and methodologies, right? The standard model of particle physics underlies all the different areas of physics. If you have a physics theory of, atomic physics, okay? You have a specific thing going on in atomic physics, and it violates the rules of the standard model of particle physics, then either you're wrong or you're going to win the Nobel Prize. There's no sense in which you just go on and say, it's a different field, right? They're all sharing that same common core. And furthermore, the methodologies and the standards and the questions that are interesting are more or less common. Physics is remarkably unified, considering how much ground it covers. And that comes down to the fact that physics is pretty simple compared to other things. Physics is all about simplifying things as much as we possibly can. And other sciences, other areas of science don't have that privilege. Okay, I'm going to group two questions together. One is from Austin Hughes, who asks a priority question. While quantum mechanical behavior is very different from our everyday experience, but the theory is incredibly good at making predictions, how confident are physicists that this is a real description of reality, or an emergent phenomenon maybe from some lower level description of reality? Is it ever possible to say that a theory is the lowest level description of reality versus a description of an emergent phenomenon? And then the other question is from Sid Huff, who says, do physicists know for certain that quarks are not made of something even smaller, and why? So you see, Sid's question is a more specific version of Austin's question. And the answer is we don't know. We arguably will never know for sure whether or not our current best theory of the world is the fundamental theory, is the absolutely correct theory. You have to be open-minded about the fact that you might discover some new phenomenon that you didn't predict in your underlying theory. But what we do know is that right now we don't have it. We do not have that underlying theory of everything because we have general relativity and we have quantum mechanics and they're incompatible with each other. You would think that different parts of physics need to be ultimately compatible with each other because they all are describing the world in some way. It might turn out that the best description of the world is a patchwork quilt where the patches overlap with each other, but they can't be incompatible in regions where they should both be true. And that's the current situation with general relativity and quantum mechanics. So, we can look for ever deeper levels, but the point is not there is a level that is the deepest and we need to find that, right? If we keep finding deeper levels, that's fine. If we find a level that seems to be a theory that covers everything, that's also fine. And we can also keep looking for even deeper levels after that. The specific question for quarks, people have absolutely thought of the idea that quarks are made out of smaller constituents. In fact, there's even a name for it. It's the idea of a preon, P-R-E-O-N, not a prion, which is a neuroscience concept. Preons are hypothetical little particles that are inside quarks in some sense. So you can try, right? You can try to build a model of preons inside quarks, compare it to the data, etc. It doesn't seem to work. As far as anyone knows, it doesn't really work yet. Maybe we just haven't been clever enough yet. But I think that the smart money is betting the quarks really are fundamental, at least as far as field theory is concerned. Abby Levine says, it seems that space expands everywhere except, e.g., in galaxies. Is it that interstellar expansion is negligible compared to intergalactic and larger scales, or is it literally zero? So of those two options, it's closer to saying it's literally zero, but there's a more subtle answer here. When we talk about the expansion of space, we are talking about cosmology, and in fact, we are specifically talking about the approximation we use in cosmology, that you can divide all of space-time, as we said before, into space and time, assign a geometry to space, and talk about how that geometry of space changes over time. And since the assumption is that the universe is homogeneous, it's the same everywhere, in this approximation, we're making that assumption, it's the same curvature of space everywhere, and it either just increases or decreases. And we call that the expansion of the universe or the contraction of the universe, if that were to happen. But of course, we know that in the real world, that's just an approximation. And that approximation breaks down when you get to the level of inside a galaxy. Inside a galaxy, it would be a terrible approximation to think that the density of the galaxy is the same as the density of the universe or intergalactic space. So the real point is that the metric of space-time inside a galaxy is not in any sense well approximated by attributing a constant curvature to space. The curvature is different in different places. It's different inside the sun, outside the sun, inside a black hole, far away from the galaxy, near the rim of the galaxy, whether a gravitational wave is passing by, whether two neutron stars are orbiting each other. All these weird, crazy things are happening in a very, very location-dependent way. So the idea that there's one thing called the curvature of space that has a number that either increases or decreases is just wildly inaccurate, okay? So inside a galaxy, and this is a more full answer that I've ever given to this question. I've been answered this question lots of times. This is the fullest answer I've given to it. It's just conceptually wrong to talk about the expansion of space. What you should talk about is the curvature of space-time in the galaxy, okay? And that you can do, and it's complicated because there's lots of stars and lots of gravitational fields, but remember the curvature of space-time is what gives rise to what we think of as the gravitational field. So when you're talking about the space-time curvature within a galaxy, you need to separately treat every star and planet, right? Because they're all sources for space-time curvature. Now, having said that, so this is all a way of saying you really shouldn't even talk about the expansion of space inside a galaxy. But there's also an additional bit of intuition that you can get, which is the following. If you take an expanding universe, which is completely smooth and homogeneous, and take a region of that universe, imagine that it's like made of dust. Dust is what cosmologists call particles that are not moving, okay? Individual particles scattered uniformly through space, but they're not moving with respect to each other. So space is expanding, the particles are moving apart. Take all those particles in a spherical region of space and squeeze them into the center of that spherical region, leaving a gap, leaving empty space in between the center of that region where now you've made a collection, a clump, and the rest of the universe going on its own way. You can exactly solve Einstein's equation for this kind of situation where you have a clump of stuff orbiting itself, much like a galaxy, and then you have a region of empty space, a spherical annulus around that clump, and then past some boundary, you have a uniform collection of matter. The uniform collection of matter continues to expand. It is unaffected by a spherical concentration of matter replacing a spherical region of uniform dust, okay? And the galaxy that you made, the clump of particles, is completely unaffected by the fact that the rest of the universe is expanding. 100% zero unaffected. There's literally it's not an approximation. It's not pretty close. It's not negligible. It's zero effect of a spherically symmetric expanding universe around it. So to the extent that that thought experiment is a more or less useful guide to what happens in real galaxies, as if we consider the rest of the universe outside the galaxy as still being completely smooth and homogeneous, but inside we're a clump of matter surrounded by empty space, there is zero effect of the expansion of the universe on what happens inside a galaxy. And that's more or less true in the real world in our actual galaxy. Alexander Cordova says, if you were close enough to two colliding black holes or neutron stars, would you be able to see the gravitational waves rippling off? I'm guessing the timescales here may not be human-friendly, but assuming we could take a video and play it backward, and play it back in fast-forward or slow motion, could you actually see the ripples moving outward? No, certainly not. It's gravitational waves. The only thing you can ever see are electromagnetic waves. That's what it means to see. You're looking with your eyes that see light. And a gravitational wave puts off zero light. If you surrounded the inspiraling objects with other objects, planets or stars or whatever, then you could see that they would move with respect to each other. But you're looking at those planets and stars. You're not looking at the gravitational distortions directly. Jeff B. says, I would love to be able to dive deeper into physics and many other challenging subjects, but I find that I lack the energy after coming home from work. Do I just need to suck it up and get reading, or is there a way to make learning challenging concepts feel like less of a chore? Mostly you got to suck it up, I think, is the answer here. I don't think that there are any tricks to making learning challenging concepts any easier. When you say that it feels like a chore, what does that mean exactly? Because you just said you'd love to be able to dive deeper into it, but then you say it's a chore. So, maybe it is just a chore. Maybe it's not something that you're really interested in diving deeper into. Maybe you just wanted to have happened. And there's just no way to make that happen. Because when you're learning something like this, you're retraining your brain. Your brain doesn't naturally go down those routes that you need to go to learn about modern physics or any other academic subject, really. So it's hard, and it requires, practice and thought and also repetition, doing problems, working out things for yourself, et cetera, et cetera. You can do it in bite-sized chunks rather than trying to do it all at once. You need to, if you're learning, as we already talked about, the curriculum, right? Classical mechanics, electromagnetism, et cetera. And every one of those subjects, of course, has many sub-subjects, okay? If you think of learning a little bit of a sub-subject as a goal in itself, rather than saying, I just want to learn all the physics, that's too much. Break it down into smaller pieces, and then maybe you'll feel a sense of accomplishment when you just get a little bit into it. It's the best I can offer. Casey Mahone says, David Eagleman had an idea I thought was fascinating. To be clear, he did not claim to believe it. The idea is that the brain is analogous to a radio. If you only studied the radio itself, you would never be able to understand where the sounds it made were coming from. So maybe consciousness works in a similar way, where we can never understand it simply by studying the brain. To preempt your possible response, we should be able to detect the presence of any consciousness field that pervades space, but perhaps the brain is reading some type of signal that appears scrambled or encrypted unless interpreted by a brain-like structure. So, as usual, the answer is anything's possible, maybe. David is describing not a new idea, but an ancient one. I mean, this is the idea that, not ancient, maybe it is ancient, but it's certainly very old. This is Descartes' idea. Descartes was a card-carrying dualist. He thought that the mind was completely separate from the body and was indeed not even physical or located in space at all. And he had this idea that there was a radio receiver, he didn't call it that, but basically a radio receiver in the pineal gland in the brain that communicated thoughts and feelings to and from the mind and the actual body. It doesn't work for lots of reasons, for many, many, many reasons. But the simplest one today is that, as I've often said, we know too much about the physics of the particles that make up the brain. In order for something like this scheme to work, even if it's encrypted, et cetera, you have to change the laws of physics. And we have very, very good experimental data that says that the laws of physics, when it comes to atoms and electrons and molecules, et cetera, are very, very well understood. Again, it's possible, but there's zero evidence for it, lots of evidence against it. Joshua Hillerup says, how common is it for physicists working in your area these days to discover facts about the universe that get basically confirmed as being true? Where on the spectrum is it from every working physicist should be doing this fairly often to if you manage to do this, you win a Nobel Prize? Well, I think the key phrase here is in your areas. In most areas of science, working physicists do discover new facts about the universe. The facts might not be that profound, right? Like if you have a new material that you made out of atoms in a certain new crystalline configuration, and you measure its tensile strength or its electrical conductivity, boom, you've discovered a new fact about the universe, okay? Real physicists and real biologists and chemists, et cetera, do things like this all the time. That's their job. They discover these new facts about the universe. Now, these facts are not facts about fundamental physics, as we like to call it, or elementary physics, if you want to be a little bit more humble about the whole thing. The basic laws of nature, right? The core theory, the standard model of particle physics plus general relativity, that is something that's been in place since the 70s. The only things we've done since then are discover parts of it. So we've measured the mass of the Higgs boson, but the Higgs boson idea was invented in the 60s. We measured the cosmological constant, right? The vacuum energy. We thought it was zero, but we discovered it. So we knew that it could be there. It was proposed by Einstein in 1917, but we measured its value. A lot of people thought it would be zero. And likewise, masses of neutrinos are something that sneaked up on us gradually, through the 70s, 80s, 90s, and now we have some more data about them. But the basic structures that allowed all this to happen have been there since the 70s or earlier. So no, people in my areas do not discover new facts about the universe. To discover a new fact about the fundamental laws of physics is something that, if it goes on like this, soon all the people who have done it will no longer be with us. Steven Weinberg did it, right, as a theoretical physicist. He discovered how to unify electromagnetism with the weak nuclear force, but he passed away recently. So yes, these days in fundamental physics, if you discover a new fact about the universe, you would absolutely win a Nobel Prize. Siddhartha says, it's been a while since I last saw you in a theism versus atheism debate on YouTube. Do you think the ideas and arguments supporting atheistic worldview are so sufficiently widespread today you don't need to anymore? Or did the debate format stop being that interesting and effective? A combination, but I think also I just haven't been invited to any. I don't think there are that many. Like, I don't set up these debates. I have a mixed feeling about public debates. It's not really a way to reach any conclusions, right? When I participate in one of these debates, I'm not trying to win the debate. I'm not trying to score points and come out on top on some judge's ballot, nor am I trying to persuade the person I'm debating, because usually they're very, very, very set in their ways, as, to be fair, I'm very set in my ways if I'm actually having a debate about these things. What you want to do is reach the audience. There are people in the audience who have not made up their minds about these questions. So I think that there is a useful purpose to these debates, but it's not finding the truth. It is educating the audience about ideas you already have. Look, I'm busy. I give a lot of talks, things like that. Recently, the talks that I've been invited to give have not been debates. They've just been talks. I have no objection to the idea, but, I've said a lot of what I want to say in that format. So it would have to be interesting for some reason for me to do it again. Charlie Grover asks a question about the swampland. So it's a long question. I'm going to try to make it a little bit shorter. But he says, Qumran Vafa and other prominent string theorists have recently been working a lot on these swampland conjectures. And so to put it in my own words, the idea of the swampland is we have this idea of low energy effective field theory. Okay, so we have field theories, including the standard model, but also extensions of the standard model. You can include supersymmetry or dark matter or whatever. All of these are low energy effective field theories. They're not supposed to be theories of everything. They're theories of particle physics and quantum fields at low energies. And there's millions of them, an infinite number you can easily invent. The swampland conjecture says that not all theories of low energy particle physics that you can invent can be derived or can be made compatible with quantum gravity, and in particular string theories, because they think that quantum gravity is string theory, generally the people who do this. So the swampland language was invented to contrast with a landscape, okay? The string theory landscape is this set of very large number, Numbers like 10 to the 500 are bandied about, but we don't really know. Very large number of possible low energy theories that you can derive from string theory. And the idea behind the swampland conjecture is, well, if there is a finite number that you can, or even if there is a sort of parameterized finite dimensional set of theories you can derive from string theory, and there's a whole bunch of other theories you can't. And maybe we can learn something about either string theory or about nature by understanding the difference between these. And sorry, I'm putting words in Charlie's mouth. Sorry about this, but the question he focuses in on is that of the cosmological constant. It has turned out to be extremely hard within string theory to come up with low energy effective field theories where the cosmological constant is positive. So remember, string theory starts as a theory of strings, or maybe a theory of membranes or things like that, but in a higher number of space-time dimensions, either 10 or 11, depending on the version or the limit that you're taking in string theory, but more than 4 that we live in. So you have to compactify these extra dimensions. And when you compactify the extra dimensions, it affects all the parameters of your low energy theory, the mass of the electron, the charge, the fine structure constant, and also the vacuum energy. And so far, not only have we not rigorously established the existence of some compactification of the extra dimensions, which leaves the cosmological constant positive, there are general arguments that you can't. Now, these general arguments are not airtight. So there are people, I should say, who have claimed to suggest ways you can make compactifications of string theory with a positive cosmological constant. There's a famous paper called KKLT, after the initials of its authors. If I can remember correctly, Contru, Kalosh, Linde, and Trivedi. And then many follow-up papers from that where they proposed that they could do it. They could get a compactification of string theory with a positive cosmological constant. Others don't think it works. They disagree with this paper, okay? So despite it being theoretical physics, there's room for disagreement there. Okay, so all of this is a long warm-up to saying that there are still string theorists who think that string theory is incompatible with the positive vacuum energy, full stop, in the low-energy effective field theory. And you might say, well, then string theory is ruled out because we've measured the acceleration of the universe and the cosmological constant is positive. But not so fast. There is, of course, the possibility that the acceleration of the universe is not due to the cosmological constant, but due to a dynamical form of dark energy, right? Sometimes the leading candidate would be quintessence, would be a scalar field slowly rolling down a potential. Now, I've written about quintessence. I thought a lot about it back in the day. I was the first one to really emphasize the fact that if you have these quintessence fields, they should couple to other fields. They should couple to the standard model fields and be detectable for that reason. But I also pointed out the loopholes in that argument, how you could construct quintessence fields that were not detectable. But generally, if quintessence were the dark energy, it would have been easy to already have detected it, to already have either measured it directly through couplings to other fields or indirectly through the expansion of the universe. And we haven't yet. So whatever your credence is in quintessence versus cosmological constant, it's lower now than it was 20 years ago when we started playing these games. So the question, Charlie's question, is, what about this theoretical argument from string theory, which leaves open the possibility of quintessence, but seems to be against the cosmological constant? So I don't take it very seriously, that particular argument, honestly. I don't know enough about it to really be qualified to take it seriously or not, but my impression is that the game being played of looking at compactifications of string theory is a sufficiently hard game to play that making these very, very general statements about what is and is not possible is a bit premature. So I'm not at all convinced that string theory really is incompatible with compactifications that give you a positive vacuum energy. So it hasn't changed my credences that much. But, look, I'd be delighted if the dark energy were quintessence. In fact, as I previously mentioned very briefly, if it's quintessence that is a pseudo-scalar field, that could cause cosmological birefringence, and I'd be famous because I predicted that. So my vested interests are in favor of it. But, I love the idea of the swampland program because it is a real good faith, honest attempt to connect string theory to observational and experimental physics. And however you can do that is a good thing. Vladislav Liutka, I hope I got that right, asks a priority question. What would be your credences that there are horrible inner experiences associated with a person who is having surgery under successfully applied general anesthesia? Assume there are inner experiences associated with conscious people, and maybe you mean unconscious people. Maybe you mean conscious people. You just mean assume that inner experiences are real things, and there are no inner experiences associated with dead people without brain activity. I think my credences would be pretty low because we have some data, namely dreaming, right? Dreaming is not exactly the same as being under general anesthesia, but it seems perfectly plausible to say that in the absence of other data, whatever experiences we have when we're not conscious might be very much like, or at least bear family resemblances to, the experiences we have when we're dreaming. What I really expect is that general anesthesia, and again, not enough of an expert to have a firm opinion about this, but my feeling would be that general anesthesia puts you under so deeply that you don't have experiences, right? You don't have anything that you would recognize as an experience. Just as you don't when you're asleep and not dreaming, that you can be asleep and not dreaming, right? So together with the fact that I think there probably are no experiences when you're under general anesthetic, and whatever experiences you do have, I'm guessing are more analogous to dreams than to horrible tortures, my credence that there are such horrible inner tortures is pretty small. And I should say, obviously the potential benefits of surgery to your waking self could be very, very large. So I wouldn't use this as an excuse to not put yourself under general anesthetic for important surgery. Maybe considerations like this are, make you think twice about elective surgery. But look, as with always with these arguments that seem to be low credence, focusing on low credence possibilities, there's also the possibility you have blissful nirvana experiences under general anesthetic, right? And you'd be depriving yourself of those by not going under. So I'm not quite sure where to balance that out. Alexandra Zani says, you've said we have reason to be confident the laws of physics underlying the phenomena of everyday life are completely known, but you and others have written books about a variety of physical phenomena we do not fully understand yet. And so the specific arrangements of the particles in those books is caused by said poorly understood phenomena. So don't we need more physics to fully explain the arrangement of particles in the everyday phenomena of many physics books? Sure. Obviously. I've never said that physics is done. I've never said we don't need more physics. What I said is the kind of physics that we need is not of the form laws of physics underlying everyday life at the level of the core theory of quantum field theory. That part of physics is done. The way that those core fields come together to make complicated things like books and people, obviously completely unknown, or not completely unknown, but very far from being completely established. And we have a lot of work to do on that. Those two statements are utterly compatible. Aurea Biddle says, in your podcast with Neil Ferguson, he mentioned the fact that it is easy to place all the blame on individual actors for failures to meet demands during a catastrophe. And instead, he opted to emphasize the role of networks and how our lack of native vigilance can cause dysfunction. In regards to COVID, however, he seemed to be downplaying the role that one man, Donald Trump, material had in politicizing and therefore swaying the Republican response and messaging around the crisis. Is it not valid to blame the spearhead as a useful shorthand when trying to troubleshoot how best not to repeat these same errors? Well, so I think a couple things are going on here. I mean, one, Neil is not being inconsistent, right? He's saying we're too tempted to blame individuals, and in this case, he's not blaming an individual, so that's completely consistent. Now, what you're suggesting is maybe there is a sense in which we should be blaming an individual in this case, and regardless of the specific details of this moment in history, I think as a general question, can individuals be blamed for bad responses to catastrophes? I think it's a complicated question because I think that This is in the nature of complex systems. I think that probably I'd be sympathetic to the direction of Neil's critique, namely that we are more likely to blame individuals and less likely to blame systems than we should be. I don't think that that means we should not blame individuals at all, right? The system of which Donald Trump was a part is very complicated, and there's a lot of inertia in it and a lot of moving parts. And there's only so much impact that one person can have, even the president of the United States, Having said that, some people have a lot more impact than other people do, and powerful politicians and business people, et cetera, have more impact, have more power in this system. And it is 100% okay, in my mind, to blame them for the responsibility that they deserve to have. So, those are all fuzzy words, and there's a quantitative question of how much blame to place. But, I am sympathetic with the general idea that too often we personalize the blame because it's much easier emotionally to place blame on a person than it is on institutions and systems. Stuart Haynes says, when I sort your YouTube videos by views, I see that many of the biggest ideas in the universe videos have the most views. Did you think that series would be that successful, and which of your videos have been the most surprisingly popular, or on the other hand, surprisingly not so popular, and why? Basically, my videos on YouTube fall into 4 categories. One category is the biggest ideas series, which has 48 videos. One is the Mindscape podcast, which I put on YouTube as a favor to the people of YouTube. And I get, 5,000 views. It's not a lot. But it's exactly the podcast, and there's no video. It's just an image, a static image. And I have no understanding of why people would rather listen to the audio on YouTube rather than on some podcast app. Even if you're sitting at your desktop, you can listen to the podcast either on preposterousuniverse.com or on Apple Podcasts or whatever. But some people really like YouTube. Okay, that's fine. Then the only other long series of videos I did were the Moving Naturalism Forward conference videos. I mentioned this workshop we did, and we videoed all that, and that's all been edited very nicely by Gia Mora, and it's been put on the web in bite-sized chunks. And finally, just a couple of miscellaneous videos that are not really worth even mentioning. So I'm not at all surprised that the biggest ideas did much better than the Mindscape videos. Because look, the Mindscape videos, I don't get any benefit from them. It's just extra work for me. I don't even get paid. Like when someone listens to the podcast on a podcast app, my podcast my podcast network, Wondery, counts that as a download, and it charges the advertisers. And so I get a penny or whatever it is for every one of those times that someone listens on a podcast app. I do not get money from the advertisers on YouTube when someone watches on YouTube. I do get money from YouTube ads, but that's like an order of magnitude less. YouTube is not, you're not doing YouTube for the money at my level. Like once you get millions of hits, then maybe doing YouTube videos is worth your while, but for 5,000 hits, it's really not, you're not, buying an ice cream cone for that, much less quitting your job. So I just do it because I know that people like doing it on YouTube, and I want the podcast to reach as many people as possible. That's why I do it. But I wouldn't watch Mindscape. I wouldn't do Mindscape on YouTube. I would do it on a podcast app. So I'm not at all surprised that the biggest ideas videos, which were meant to be seen on YouTube and have visuals, do much better than the Mindscape videos. I do wish that the Moving Naturalism Forward videos had done better. They did very badly in terms of numbers, and I'm not sure why. We had famous people there saying interesting things, and the videos themselves were, I think, very nicely done. Hired a professional videographer and so forth. So I think there's a lot of treasures in there that hadn't been appreciated by the wider folks. Lineo Miziara says, how does David Wallace's explanation for probability in many worlds differ from yours? Well, I think it's ultimately completely compatible. Chip Stevens and I wrote a couple papers on probability in many worlds using self-locating uncertainty. And we emphasized from the start that we weren't doing it because we thought that other people's explanations were wrong. If there's one true fact, it's very often the case you could explain that true fact in different ways, using different words, but still be a true explanation in some sense, right? Having said that, they're sort of, they feel very different. And the reason why I like ours is because it sort of not just gives you the right answer, but in my mind, it gives you a better feeling for why there is probability at all. In some sense, you couldn't possibly get the wrong answer. If you put in a good faith effort to understand probability in many worlds, the only thing you're ever going to get out is the Born rule. It's just the only thing that makes sense over, consistently over time and things like that, and add, all the probabilities add to 1, etc. You're going to get the Born rule. The real question is why you have probability at all. And the approach that David Wallace has, that was based on ideas by David Deutsch, is very, very instrumentalist in some sense. The idea is, look, here we are in quantum mechanics. In fact, Deutsch's original paper doesn't even really necessarily need many worlds. He just needs quantum mechanics. And he says if there were, basically, sorry, I don't want to go into, it's getting late. I don't want to go into too many details here, but his idea is that if there are outcomes for quantum mechanical measurements that you value differently, you'd be happy if the spin was up, less happy if the spin was down. Then what you could show is that using decision theory, which says that, among other assumptions of decision theory, if you play games with probabilities, you should be just as happy with playing a game that gives you 100% probability of giving you value 1 as you should be with playing a game that gives you 50% probability of value 0 and 50% probability of value 2. Now, you might say, well, no, I'm risk averse. I like getting the 1 with 100% probability rather than the 50% probability of getting 2. But that's because you're not really appreciating the word value here. Value doesn't mean money. Value literally means that value 2, the meaning of the phrase value 2 in decision theory is you give 50% chance of value 2 equal value as 100% chance of value 1. That's what it means, okay? And what Deutsch argues and what David Wallace follows up to fill in some of the details and make it a little bit more rigorous is that given that there are probabilistic outcomes in quantum mechanics, decision theory tells us that we should act as if the probability of getting different outcomes obeys the Born rule, okay? So that's great. I mean, that's absolutely 100% compatible with how I think about decision theory and quantum mechanics and many worlds. We should act as if there is really a truly stochastic process with a probability given by the Born rule. Okay. But it doesn't really scratch the itch of saying, I want to know why there's probabilities at all. And Chip and I, following on ideas from Lev Weidman, pinpoint where the necessity of probability is, namely in the self-locating uncertainty that you don't know which branch you're on. And all of the words we use and all the metaphysical moves we use sound very different than the Deutsch and Wallace construction, but they get the same answers. So they're compatible, but I think that ours is a little bit more satisfying at explaining why you should think about the world in probabilities at all. Theirs is extremely, extremely good at saying if you do think about many worlds in terms of probabilities, it had better be the Born rule. Brad Malt says, in Something Deeply Hidden, you present a Socratic dialogue between Alice and her father in which they debate whether the number of worlds is finite or infinite and conclude the answer is not known. Can you explain how the answer could be anything other than infinite? For example, the probability distribution associated with many wave functions is a continuous curve, like the position of 2 electrons. Since an infinite number of points can fit on a continuous curve, when the wave function collapses, an infinite number of worlds must be created. So, yeah, but you've assumed a model of electrons. Namely, you've assumed that the electron can be classically described as a point particle moving in a continuum. And that might not be true. Indeed, in quantum gravity, it wouldn't be true. In quantum gravity, if what we said before about the dimensionality of Hilbert space is correct, treating fields and particles as living in a continuum is just a good approximation valid at low energies. It's not exactly true. I mean, consider that when you actually measure the position of an electron, you don't do so with infinite precision, right? A real measuring apparatus has some error bars, has some precision associated with it. And of course, we can imagine that precision getting better and better. But when it gets down to quantum gravity scales, maybe the whole idea of doing that measurement just breaks down and isn't good anymore. So you're right. What you're putting your finger on is the idea that if the model of an electron as a classically starting as a point particle on a continuum and then quantizing that would give you an infinite dimensional Hilbert space, and the number of worlds could be infinite. But nature might not be like that because nature has gravity in it, so we just don't know is the correct answer right now. DMI says, if regions across which a function can be analytically continued all contain the same information about the function, and if quantum fields have analytic properties, and if unitary information is contained in quantum fields, then how can a black hole in one region cause the information in different regions outside the event horizon to be paradoxically destroyed? I don't think the quantum fields have analytic properties. There's no reason for them to. I mean, it may be that in some particular state, quantum fields have analytic properties, but in an arbitrary state, they don't. So for those of you who don't know, in functional analysis, in differential equations and subset differential equations that thinks about the properties of functions, there is a very, very, very special kind of function called an analytic function. And analytic functions have the properties that in some small region, between x equals 10 and 11, I give you exactly what the function does between x equals 10 and x equals 11. And the analyticity is a property of functions that they may or may not have, such that if they have it, then the data of what the function is doing between x equals 10 and x equals 11 is sufficient to tell you what x is doing at what the function is doing at x equals 12 or 13 or 14 or minus 12 or a billion or anything else, everywhere else, okay? So analytic functions are very, 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 very special functions. Most functions, if I just tell you what the function does between 10 and 11, it doesn't tell you anything about what the function does anywhere else. So often in physics, in special circumstances like the vacuum of a quantum field theory, it's nice to imagine that our functions are analytic. It tells us something about what they're doing all over the place. But the whole point of the black hole information problem is that we're not in the vacuum. We have a black hole. We've dumped some information into it. And once that happens, there's no reason to think that the behavior of a function in one region of space tells you what the function is doing elsewhere. So I don't think that there's any relevance to the black hole information puzzle. Maxwell's Demon asks a priority question. Is there a path into physics higher education for someone who self-studies despite getting an undergrad degree in a different subject? To clarify, this question is more about the actual path to higher ed, assuming I'm able to attain proficiency, but if you have tips on learning, that would be great also. Right, so I should have grouped this with the previous question, but that was mostly about learning. This is about the path to higher ed. Let's remember the typical path for an academic physicist. You get an undergraduate degree, you get a graduate degree, you get a postdoctoral research position, and then you get a faculty job, and ultimately you get tenure. And then you get elected to the National Academy and win the Nobel Prize. Who knows what will happen after those? But those are the typical career steps. So in principle, you can get in at any level, right? In principle. It becomes harder and harder to get in the higher the levels are because there's just very few resources. There are fewer faculty jobs than there are undergraduate student positions, right? So if you get an undergraduate degree in a different field than physics, but then study physics, it's possible to get into grad school. You just need to convince some department that they should admit you. And that actually often happens, believe it or not. Departments are kind of morbidly curious about people with different backgrounds, and they might be skeptical at first, but if you can convince them that you would do well in grad school, then they would often be happy to take a chance. Remember, you can apply to 50 grad schools, and you only need one to take you. How do you demonstrate that proficiency? The simplest way is to really get a killer score on the physics GREs, right? That's one simple way. But maybe there are other ways, letters of recommendation or something like that you could do it. If you thought that you were already advanced enough to be at the equivalent of already having a PhD, and instead you were not applying to grad schools but wanted to apply for jobs, for postdoc jobs or for faculty jobs, very often into postdoc job ads, there is a requirement that you have a PhD. And they're not trying to be gatekeepers, keeping out, rogue physicists who've taught themselves. They just don't want people who are, undergrads to skip the PhD step, right? They want people to get that training. But I can imagine you could convince someone to hire you as a postdoc if you didn't have a PhD. And the way to do it is write really good physics papers. Get them published in journals. If you write a really good physics paper, submit them to the physical review, they will, if it's a sensible paper, they will get it refereed and publish it. And if you have a track record of publishing good papers, then people will be interested in hiring you. I mean, in math, this actually happens, right? In math, there are stories of people who are completely untrained but are just geniuses and do great things, and then everyone wants to hire them. It's easier said than done. It's very, very hard to do because the training that you get in school is not just in the subject matter, but all that informal folk wisdom that you soak up from being in the environment and having an advisor and talking to students and doing collaborative research and things like that. So it's hard, but it's not impossible. Vincent Ohm says, is there a non-physical aspect to information? Suppose we have 2 book pages. One contains the theory of everything in a language we do not understand, and the other contains the recipe for an apple pie in English. Does the latter have a higher information content just because we can read and understand it? Well, guess what? It's going to depend on your definition of the word information. And that definition, I know you should say yes, but I can look it up in a dictionary or so forth. But we use words like information differently in different contexts. So one definition of information is a correlation between one physical configuration and another one, right? So if I have a photograph, okay, that photograph contains information because there is a strong correlation between the image in that photograph and the image of the thing I took a picture of, right? And there's no interpretive step involved in something like that. It's just a true fact. And I can absolutely say that's information. Even if there was no one looking at the picture, whoever would look at the picture, the information is still there. So therefore, in that sense, if I had an untranslatable manuscript, if it really does say something correct about the real world, it contains information. Absolutely. Now, that information might be inaccessible to us, so there might be another notion of information, which is something like the accessible information, right? The usable information. And that might be much, much less. So, if you take a book and burn it, as we previously talked about in the podcast, at the level of fundamental physics, information is conserved. The positions of all the atoms and the molecules in the book, which contained information, is in principle still there after you burned it. But in practice, you're not getting it back. So in practice, you burned that information. You destroyed it. So in that sense, that's the sense in which having a text in a language that you can't translate, you might as well not have any information that's accessible at all. Okay, I'm going to group 2 questions together. Anonymous says, Alice is a character in a fantasy world, and she can do magic. She's helping Bob, a farmer, by using her magic to teleport his cows across a river. Alice knows 2 kinds of teleport spell. The first kind of spell works like a Star Trek transporter. She destroys the cow and creates an exact copy of the other side of the river. The second type of spell targets the fabric of space-time and temporarily connects the cow's location via a wormhole, I suppose, with the new location on the other side of the river. Though Alice can perform impossible feats, her magic still follows rules and comes with limitations, and she wants to be as efficient as possible. If the complexity and difficulty of her spell is proportional to the complexity and difficulty of the change she's trying to make in reality, which spell is easier and uses less energy? You can assume spherical cows. Thank you for letting me assume spherical cows. That's very helpful. And then Matt Hickman says, if I take a Star Trek transporter from location A to B, did I die at location A and a new being get created by B at B with my memories? And does your answer vary depending on transporter implementation? That's why I grouped these 2 together. So first to Matt's, actually I should probably group Matt's together with the previous question about the self in many worlds, now that I think about it, but I don't think you died. I mean, the question is, so let's back up. If you take a teleporter machine, transporter machine, so you disappear at one location and you're reassembled at another one, okay? One attitude would be there is some essence to yourself that is physically attached to your body, and that essence ceases to be attached to your body when you transport, and therefore you die. And the thing that is assembled at the other location is something that looks like you, talks like you, has all your memories, but it doesn't have that essence, so it's not you. As you might guess, this is not my view. I don't think there are any such essences. I think that the world is the stuff in it and what the stuff is doing. So to me, the fact that I disappeared here and appeared somewhere else because of the transporter machine, it doesn't affect any of the reasons why I would conventionally think of my future self as part of the same person as my past self, right? Technically, they're different selves, but I don't think that I'm dying at literally every moment and then a new person is coming into existence. I attach some continuity to them. And all of the reasons why I might attach that continuity to them work just as well in the transporter case. If you have a duplicator machine, it's trickier, but I think in the transporter machine, I don't think of yourself as dying. So to Anonymous's question, it's an interesting question. Of course, there's no right answer to this because it's a fantasy question. You've already violated the rules of physics to have this transporter machine and wormhole, at least the rules of physics as we understand them, and magic, et cetera, et cetera. So, but okay, let's play the game by the postulates that were being given here and think about it in its own terms. So I would say my guess, my inclination, my first thought is that the wormhole answer versus the transporter answer, the wormhole answer is easier. The wormhole procedure is more efficient than the transporter machine. So, and here's why, because in some sense, it is using the existing laws of physics to help it along. I mean, forget about the transporter, forget about the other side of the river, right? In some sense, here I am now, and here I am a second later, right? My body, all of its atoms, etc., exist and are related to each other. The configuration of all those atoms and all the organs in my body at one moment of time is related, but not the same as the configuration of all that stuff 1 second later, especially if I'm moving and talking and things like that, okay? But it didn't take any effort for me to be in almost the same configuration 1 second later. It just happened because the laws of physics did it. And I think that if you go to the effort of building a wormhole or a bridge through space-time, then the sort of nuanced effort of moving each individual atom and molecule in the body of the cow is done by the laws of physics. It goes along for the ride. Whereas if you need a transporter machine, well, you haven't told me the technology behind your transporter machine, but somehow I have the feeling that you're sending the cow molecule by molecule. You're not letting the laws of physics move the positions and velocities of all the parts of the cow. You have to do it by hand in some sense. So that seems a lot less efficient to me. But to be honest, I am much less clear on what the technology of the transporter machine would be than I am on the technology of the wormhole. Okay, Bill Hughes asks a priority question. In Something Deeply Hidden, you've said that many worlds doesn't violate conservation of energy because each of the child branches is thinner because their amplitude is less. I've also heard you say that the low probability branches count for less. What real world effect does being in a branch with less amplitude have? What real thing is amplitude measuring? It's not probability because all the branches do exist, nor the likelihood of being on a branch because you are on all of them. So the answer is it's the likelihood of being on a branch. That's the real world effect of the amplitude. And I know you just said it can't be that because you are on all of them, but you're not on all of them. Different people are on all of them. That's the point. I mean, if you don't accept that, that's fine, but then you're just not going to accept many worlds at all, and you should develop some metaphysical objections to it. But what the many worlds person says is that once the branching happens and you have different worlds, the different people on those different worlds are different people. They're not you on all of them. So there is a question after the branching happens. If I exist after the branching and I know that I'm on one branch but not the others, which one am I on? And I assign a probability, and that probability is given by the amplitude squared. That's the relevance of the amplitude. Russell Wolfe says, what is your opinion on the use of the word energy in a psychological context? Like when we talk about extroverts gaining energy from social interactions, while introverts are drained of energy and need to recharge. Is there a meaningful physical definition of energy that matches this colloquial use of the word? I'm completely fine with that use of energy. Look, I take yoga classes, or I haven't in a long time, but I am all in favor of taking yoga classes where the instructors often use all sorts of crazy words to describe what is going on. I don't care. Who cares? It's a metaphor, right? It's a poetic way of talking about things. So the question is this use of the word, the question in my mind would be, is the metaphorical purpose being served by using the word energy in this context? And I think the answer is absolutely yes. I mean, we get it when someone says they're high energy, they're low energy, they gain energy, they lose energy. Everyone knows what that means. And it doesn't correspond to anything, any physical stuff going into their bodies or anything like that. It has to do instead with intricate questions about their physiological state that are generally going to be very, very complex, okay? But I have no objections to that whatsoever. As long as it's clear, I'm all in favor of it. Julie Mars says, can you recommend a popular science book that explores the phenomena associated with phase transitions across many different disciplines? I've already read Complexity by Michael Waldrop, but wasn't thrilled with it. No, I can't really recommend that. I mean, there's the book by Malcolm Gladwell, The Tipping Point, right, where he tries to use notions that are kind of phase transition-y to describe some social dynamics. And, there's some things that are true that are said in that book, but it's not going to give you insight into the physics phenomena, nor how the physics phenomena can be used in broader context. I say this with regret, wistfully, because Jennifer Willett, my wife, for a while was planning to write such a book. But alas, in the real world, if you want to put a year or so of your life into the effort of writing a book, someone better buy it. And the booksellers of the world were not convinced that anyone would buy a book on phase transitions. So I don't know. I mean, there could be one out there that I don't know about. Happy to take suggestions in the comments. Igor Kopilov says, you've mentioned that you're writing a quantum mechanics textbook. How do you balance doing something new with covering all the standard things that every QM textbook has to cover? Do you reach out to colleagues who teach QM courses to get their input, or are you just following your own vision? Mostly following my own vision, but I'm certainly looking at other people's books. I'm not talking to a lot of people. I guess I've talked to a few people who have taught quantum mechanics, but there's a standard curriculum. I'm not going to be surprised by talking to people who have taught it. They use the same textbooks, et cetera, et cetera. And mostly I do want to cover the standard stuff. I'm not trying to revolutionize the teaching of quantum mechanics, but I do want to nudge it in a productive direction. So I think that there are ways in which, I think there are pretty clear ways in which the current way that we teach quantum mechanics falls short. And I don't mean they're not teaching many worlds. I don't even mean they're not teaching the foundations of quantum mechanics. I do think they should say true things about the foundations of quantum mechanics. They should be correct when talking about the measurement problem or Bell's inequality or things like that. And they're often not. Okay, so I think I can try to get that better. But more importantly, very often, quantum textbooks are just excuses to solve the Schrodinger equation over and over and over again, most often for single particle systems. And the notion that particles can be entangled is mentioned and then slid by, right? So that's terrible. That to me is just doing a disservice to what makes quantum mechanics quantum mechanics. So I think that without getting philosophical or anything like that about it, I definitely want to do a lot more than the typical quantum mechanics book does to explain both the phenomenon of entanglement and the technical apparatus that goes along with thinking about it, decoherence and density matrices and things like that. And this is not just because I think it's interesting and true, although there's that, it's also relevant to how we use quantum mechanics in the modern world. Whether we are grown-up professors, that are now doing research in quantum mechanics, or whether you go into industry to build a quantum computer. Quantum computers rely on entanglement, and it turns out that it's not that hard and enormous fun to teach people the basics of quantum information and quantum computing. That's 100% appropriate for an intro quantum course. So ideally, if it all works out, there will be stuff like that in my quantum textbook, but it will be optional. Entanglement will be there, non-optional, but then you can choose to still, spend a lot of time doing Clebsch-Gordan coefficients and additions of spins and time-dependent perturbation theory, if that's what gets your juices flowing, or you can do quantum information and quantum computing if that's what gets your juices flowing. That's the goal. We'll see if it all pans out. Gregory Kusnik says, in last month's AMA, you argued that since events at the scale of human affairs are effectively classical and deterministic, we should expect histories that diverge radically from our own, like the Nazis won World War II, to have very low probability. I don't see how this follows. It seems to me there's ample scope for quantum uncertainties in things like genetic recombination and the random activation of oncogenes to have profound effects on who gets born and who dies early. This would lead me to expect a diverse array of very different histories, all with roughly equal measure. So I think that's a fair point here, but there is a footnote that is crucial, which is when you're thinking about the wave function branching. So as you think about branchings of the wave function that go earlier and earlier in time, then you can have a tiny fluctuation, a tiny difference at very early times lead to an enormous difference in the present era. Just for the most dramatic example, if you believe in inflationary cosmology, then literally the fluctuations that led to galaxies forming are quantum measurement outcomes that would be very different in different branches of the wave function. So the Earth and our galaxy, the Milky Way galaxy, wouldn't exist in a large number of other branches of the wave function. That's certainly very different, okay? What I was thinking, what I was implicitly assuming, which I shouldn't have implicitly done, I could have done it and said it out loud, was that we were talking about branchings that were relatively recent. So I'm not even talking about who is born and who dies. I was talking about the actions taken by the leadership of the countries during the 1930s and 1940s. And I think the room for large variations is much smaller. It can happen, but I think the probability is much lower. But sure, if you are including branches that branched off a long, long time ago, even if you go back, thousands or millions of years, so that genetic histories could be very different, then yes, you could get histories now that look quite different. Johan Löfgren says, I enjoyed your recent paper, The Quantum Field Theory on Which the Everyday World Supervenes, and I find myself largely in agreement. But I'm worried that the issue of naturalness is being swept under the rug. From effective field theory principles, we expect the standard model Higgs mass and cosmological constant to be much larger than what we have measured. When we are considering the completeness of the core theory, should it not give us pause that the standard Wilsonian effective field theory principles do not seem to lead us right here? Sure. So what's going on here is I made an argument in this paper that on the basis of what we think we understand about effective field theories, we have very good reason to believe that any variations of the core theory, the standard model of particle physics plus general relativity, would be irrelevant to everyday life things, in particular things that go on in a brain or a biological organism. And crossing symmetry and other features of quantum field theory are important for that argument, but so are the idea that the dynamics of the fields we already know about is pretty well understood. So there is a weaker argument than I made that still works. Even if you don't believe the rules of, not the rules, but the expectations of effective field theory, those expectations tell us that there could be new interactions, what we call irrelevant or higher dimensional operators in the quantum field theory. But the sizes of those interactions are very, very small. That is a prediction of effective field theory. Or, so I keep saying prediction, an expectation. It's not a strong prediction. It's just we expect in a reasonable, non-finely tuned theory that these extra interactions are very small. So two things to say about that. One is we could be wrong. And what Johan is bringing up is there's two famous examples where we are wrong, the Higgs mass and the cosmological constant. Now, they're both special. Those two quantities are both special in effective field theory as relevant operators, that there are only two relevant operators that we can write down. And so it turns out that in the core theory, there are two relevant operators, and our effective field theory expectations for them are wrong in both cases. But that doesn't mean that we're wrong about marginal operators or irrelevant operators. So there's no immediate worry, but it does remind you that these are just expectations and you can be wrong about them. Okay, so to that extent, this is a perfectly good issue that Johann raises. However, it doesn't really help you, because even if you were very skeptical about that particular expectation of effective field theory, what could you get by violating the expectation of effective field theory? Well, we've already measured the coefficients of the parts of the standard model we know, right? The masses and the kinetic energies of the ordinary particles and fields. The only room for changing the dynamics of the known fields is in their higher order interactions, right? How an electron interacts with two photons at once or something like that. And the point is that even if that interaction was much larger than we expected, who cares? It's not going to affect everyday life in any interesting way, right? In order to have this kind of effect, we either need truly new fields that are pushing around the fields of the standard model in some non-obvious way, or we need something dramatically in violation of effective field theory principles, like a violation of locality. That's really what people want. The people who want to change the laws of physics in order to have an impact on consciousness, they don't care about higher order operators. What they care about is that electrons in the context of a human brain behave differently than the same electron would behave in the context of a rock. And that's not just a matter of the expectations of higher order non-renormalizable operators being off. That's just a total violation of everything we know and love about field theory. So I'm not worried about that loophole actually being exploited in nature. Herbert Berkowitz says, is there a philosophy to mathematics, or is it just one of those things that is what it is? So yeah, there's absolutely a philosophy to mathematics. You might remember that I did a podcast where we talk about it with Justin Clark Doan. We talked about the philosophy of mathematics and morality and their relationship to each other, but a lot of it was just the philosophy of mathematics. You very quickly get into questions about mathematics, like, can things be true even if you haven't proven them? What does it mean to be consistent? What kinds of transfinite numbers are there? You know, are mathematical objects real in some Platonic sense, or are they just conventional? Are they just names? There's a whole bunch of good questions in the philosophy of math. So yeah, Google it. It's out there. Brendan says, you've mentioned before that you've done casual research on information theory, and I was curious as to what about that field interests you. I tried doing some research on the topic and noticed that entropy plays a big role in information theory, but I don't quite understand why that is. Any insight into this would be great. I've written a couple papers that I wouldn't call them papers on information theory, but they're papers where information theory played a crucial role. Most obviously in my papers on emergent space-time with Charles Tsao and Spiros Mikalakis, we used mutual information quantum mutual information between degrees of freedom to define an emergent metric on space-time. So that's a pretty kind of trivial, once you know what mutual information is, not really using the heavy machinery of information theory. More interesting in that context was a paper I wrote with Stefan Leichenauer and Jason Pollock and Tony Bartolotta on the Bayesian second law of thermodynamics. I still think that this paper is more important than people give it credit for, because it's the kind of thing I like to do. It answers this question of principle that many people weren't worried about, but I think they should have been worried about. Namely, how do you deal with the fact that on the one hand, you say entropy increases. On the second hand, you say that entropy is a measure of our ignorance. And on the third hand, you learn things as you look at the world, right? Actually, Cosma Shalizi pointed this out and wrote a whole paper about it, how in some weird sense, a good Bayesian sees a reversed arrow of time, right? Because you just learn more and more about the world, and therefore the entropy of the world goes down. Now, of course, that's using a very specific epistemic notion of entropy, which is different than the thermodynamic notion that we usually mean in cosmology. So it's not actually a conflict with anything that we know, but it's an interesting question. How do you reconcile those? So the Bayesian second law, which is something that we derived, answered the question, if you take the ordinary second law of thermodynamics and include in it the fact that you can measure systems and therefore learn about them, is there some notion of something going up, some measure, some quantity like entropy that increases even though you're doing measurements? And we found yes, and we derived a rule, and it has to do with the relative entropy of different distributions, and all that is very, very information theoretic. So that was a lot of fun. We didn't really give a killer app for that. So the reason why it hasn't gotten a lot of attention is, what are you going to do with it? Right? I mean, to get other people interested in it, you need to be able to say, okay, you can use this new equation, this new theorem that you derived to do some experiment or, build something or something like that. And that we didn't quite do. We have had and have ambitions to do it, but until we do that, I can't really blame the rest of the world for not getting too excited. Frank Lehman says, is there a long-standing problem in science, mathematics, or philosophy that your colleagues treat as a huge, very difficult deal, but that you don't think is particularly serious or important? And conversely, is there a problem you think of is the utmost importance, where the consensus is that it's solved or unimportant, or maybe even not recognized as a problem? So yeah, the latter is much more true. Like, generally speaking, I'm trying to think, but I think that most problems that the scientific establishment thinks are really, really interesting. Maybe I don't think that they're really, really interesting, but I generally get it. I generally think that, there's interest in doing that. Okay. After reading your question, I tried to think of a really killer example of something everyone else cared about and I don't, but I couldn't think of one. But there are certainly things that no one else cares about, or very few people care about, that I do. The big question, obvious answer is just the foundations of quantum mechanics generally, and for that matter, the foundations of statistical mechanics and probability and cosmology and all these other things. I know it's been a long time, these days, since my most recent book is on quantum mechanics, I'm known as the many worlds guy. But 10 years ago, I was known as the arrow of time guy, because my first book, From Eternity to Here, was all about cosmology and the arrow of time. My interest in that has not gone away. And I still think that the fact that the early universe had a low entropy is really, really, really important to understand. And my cosmology buddies don't always go along with that. So what can I tell you? I have lots of questions, lots of issues along those lines. Keith says, I was recently re-listening to the James Ladyman episode on structural realism, and I found myself wondering about your current thoughts on the topic that you might share more about. I.e., is either epistemic or ontic structural realism something you find congruous with your positions on the ontological status of things like the wave function and Hilbert space? So for those of you who don't remember the episode with James Ladyman, James is one of the leading proponents of this view called structural realism. And it goes in these epistemic and ontic varieties. So what does that mean? It means that the way I think about it, and I've talked with James and I've read things that he's written and things that other people have written, and we had the podcast episode, but it's still a little subtle, and so I don't want to claim that my version of it is the consensus version of it. Not that I'm trying to be contrarian, but that my understanding might not quite be there yet. So let me say the way I understand it. Thomas Kuhn famously emphasized the fact that when we have a scientific revolution, it's not just that we improve the old theory. We very often throw away the old theory. We throw away the ontology of the old theory and replace it with something completely different. Quantum mechanics is the obvious example to that, but also something like relativity, right? In relativity, pre-relativity, we had space and time as two separate things, and now we have space-time. It's like a completely different thing, especially in general relativity, where gravity is not a force propagating on top of space-time, but a feature of space-time, a feature of the curvature of space-time. So in Kuhn's view, that revolutionary science is really throwing away the old paradigm and replacing it with something new. What the structural realists are trying to emphasize is that you're not throwing away everything. Maybe you are throwing away the ontology. Maybe you are throwing away your idea of what is the fundamental stuff of the universe, right? In classical mechanics, your fundamental stuff is some particles or some fields, and they move through space-time and obey equations. In quantum mechanics, your fundamental stuff is a wave function, which is an entirely different kind of thing. But there is some similarity. If quantum mechanics is going to be successful, at the end of the day, it better predict that the Earth goes around the sun. If general relativity is going to be successful, it had better predict the same thing. The phenomenon of the Earth going around the sun is independent of your idea of the underlying ontology, whether it's four-dimensional space-time or Newtonian space-time, classical mechanics, quantum mechanics, or whatever. So the structural realists say that the thing that is real are the things that are preserved through these transitions from one theory to another. And they talk about it in terms of the structure of what relates to what. And you could say, it's a way of mapping your fundamental theoretical formalism to your experience, to your observations, to your informal view of the world. When we say the Earth goes around the sun, what we mean is there's some observations of where the sun is in the sky and where the other planets are, and they are most easily explained by thinking of the Earth as going around the sun and rotating around its axis. So it's those relationships between different pieces of the world and the relationships between our observations and the formalism that are preserved and improved over time, not thrown away entirely and replaced with something else. So there are reasons why there's an epistemic version of this and an ontic version of this. The epistemic version is the one I think I understand and agree with, which is that this whole picture where we throw away ontologies and replace them with better ones, but keep some structures along the way, is a statement about our knowledge. It's a statement about what we human beings are doing, okay? There's something true about the world, and we're learning more and more about it. And what we're learning more and more about is not just putting more ingredients into our ontology, but it may be a completely new ontology that explains the structure a little bit better, okay? That would be epistemic structural realism. Ontic structural realism is, I think, if I understand it, again, not promising you anything there, is a bit more dramatic, trying to be the claim that these structures are what really exist. That's what ontic means, really existing, right? It's not just that we know these structures, we learn about them, but regardless of our knowledge, it's the structures that exist. I don't know what to make of that. I don't know what that would mean. Like, how does a relationship between things exist if the things don't exist? That's my worry about ontic structural realism. But epistemic structural realism, I think that James and other people have convinced me is a good way to go. But I haven't reached conclusions about these things. Once again, I keep saying this over and over again during this podcast. That's okay. Living at the boundaries of our knowledge is a fun place to hang out. Kathy Seeger says, a book that is thrown into the fire. A physicist would say that information is conserved because in principle it can be reconstructed. To reconstruct, it would be needed to hypothetically keep track of the microscopic degrees of freedom of the system and then reverse everything back in time to deduce the initial state of the book from the final state of the smoke and ashes. And also the radiation. Don't forget the radiation. But how could that work out when macroscopic systems, or in fact the universe as a whole, is asymmetric under time reversal? And during that hypothetical reconstruction process, going from higher back to lower entropy, aren't there more possibilities for the microstates on the higher entropy side of things to evolve back to? So I think there's two separate things going on here. One is the macro-micro distinction. So, whenever people talk about these thought experiments, they don't mean you're ever going to do it, or even you should ever think about trying to imagine doing it. In fact, here's why you couldn't do it. Because you say, let's capture all the information contained in the smoke and ashes and the radiation. Well, you can't, because in quantum mechanics, when you measure the position of a photon, for example, you change it, right? You collapse its wave function. So you can not actually know by doing measurements what the state of the photon was before you measured it, which is what you would need to have in order to reconstruct the book. So we're not ever talking about actually something that could be done by people, even super duper people. It's just impossible to do it. What we mean when we say the information is still there is that in the universe as a whole, the universe knows. The complete state of the universe, even though it's inaccessible to us because of the uncertainty principle, etc., the complete state of the universe contains the right information to reconstruct the book. Okay, so it's not, macroscopically, it's just inaccessible to us, and the fact that macroscopic physics is irreversible is a reflection of the fact that that information is inaccessible to us. But that's completely compatible with the microscopic physics preserving the information over time. Now, the other thing that you mentioned is, I think, a little bit more interesting and provocative. You say that, aren't there more possibilities for the microstates on the higher entropy side of things to evolve back to? So, yeah, when you're in a high entropy state, like after you've burned the book, in the macro state that you are in, there's the ash, a certain amount of radiation, blah, blah, blah. In that macro state, there are more microstates than there were in the initial book before you burned it, okay? Entropy went up. That's what you mean. So what that means is that for a typical microstate in that macro state, so if all you knew was that there was some ash, some dust, some radiation, you knew its macroscopic properties, but you didn't know its microstate, and someone gave you a specific example of that microstate and said evolved it backward, it would not evolve back into the book. The overwhelming majority of such microstates would not even evolve into lower entropy states in the past. They would evolve into higher entropy states also in the past, right? Because the information that the book used to exist and used to be in a lower entropy state is still implicit in the microstate of the ashes and smoke and radiation. It's just inaccessible to us macroscopically. So we know that it used to be there because we knew there used to be a book. But just the macroscopically accessible information is not enough for us to know that it even could be reversed into a lower entropy state, much less how to do it. P. Walder says, I often hear scientists say that life on Earth only ever originated once. Does this literally mean that there was only ever one instance of some chance chemical event which subsequently resulted in the evolution of all known bacteria, plants, etc.? If so, doesn't this point to an incredibly rare event and makes the likelihood of finding life elsewhere in the universe very, very unlikely? So, I don't think you often hear scientists say that, at least not when they're speaking carefully. What scientists like to say, or should be saying, is that all life on Earth came from a common ancestor. So there is Luca, the last universal common ancestor. We don't think that different species of life on Earth now have family trees that are completely disjoint. We think that every living organism on Earth can be traced back to Luca in some sense. That's not the same as saying that life on Earth only ever originated once. It means that if there were multiple origins, either most of them didn't survive at all, or some of them combined to make our last common ancestor. So having one universal common ancestor doesn't mean it was the first ancestor. So it's possible that, life originated 20 times, and 12 of those died out, and 8 of them sort of got together somehow to make Luca, right? I don't know, but this is a hypothetically conceivable set of events. So maybe sometimes scientists say that life on Earth only ever originated once, but we don't know that, and they shouldn't say that. Now, having said all that, it's also possible, life we think originated, who knows, 3.5 billion years ago or something like that? Maybe life is rare in its origin, but not super rare. So, maybe there's a chance of it coming into existence 1 every 500 million years. So over the course of the existence of life, it's come into existence several times. But after the first time, it was already crowded. There was already life here. And the life that came into existence either was absorbed or eliminated by the existing life. That's also possible. So I do think that, we have enough evidence to say that life doesn't appear immediately and easily. Like, we haven't made it in our test tubes, right? There's a little bit of effort involved. But I don't think we have enough information to say that it's very, very, very unlikely either. The universe is a big place. there's a number, the chance that life comes into existence, that we multiply by another number, the number of possible places life could come into existence. One of those numbers is small, the other is big, and we just don't really know what you get when you multiply them by each other. Okay, Dominic Adam Jones says, as a scientifically expert, morally serious person, how do you square the climate crisis with your willingness to fly fairly regularly? So I think the short answer is Dick Cheney was right. I'm giving Dick Cheney too much credit. Usually I give him no credit at all, though, so this should count for something. Dick Cheney, back when he was running on the presidential ticket as vice presidential candidate with George W. Bush, was asked about energy conservation, in particular individual efforts to conserve energy, right? Use better light bulbs, etc. And he said, look, that's a matter of personal virtue. He didn't consider it to be a matter of public policy. And I agree with that. I disagree with him about the public policy itself should be, but this whole idea that individuals are going to make choices about light bulbs and traveling and what car to drive seems to me to be not only irrelevant to climate change, but actively unhelpful, because it's not going to help. As we talked about with Herb Gintis, the fact that there's no point in voting if all you wanted to do was be a consequentialist. The reason why we vote is to sort of demonstrate some loyalty, or because we think it's a rule that everyone should obey in some Kantian sense, etc. But me not flying would have, strictly zero effect on the climate, right? Because the same planes would fly. Like, my choice not to fly would not affect the flight of the planes. Even if 100 people choose not to fly, it's just not going to have a big effect. The way to solve the climate crisis is through collective action. Of course it is. And collective action comes through governments and international cooperation and things like that. I think that if you're serious about the climate crisis, what you worry about is public policy, not whether an individual person is driving a gas car or an electric car or something like that. You need to think much, much, much bigger. What I want, in other words, is a system that makes it easy to treat the planet well, rather than relying on individual good deeds, which will never, ever, ever do the job. We need to incentivize systems that don't cause harm to the planet, make fossil fuels really, really expensive, incentivize alternatives, give people ways to live their lives so that the choices that make them happiest are the ones that are good for the planet. That's the kind of system we should set up, not just hectoring people into behaving well. It doesn't help. And last question for this AMA. Fabian Rosdelin says, I saw you get referenced by Rationality Rules in his video on why is there something rather than nothing. And whilst I think you agree with him there, it got me thinking, has there been any case where you felt misrepresented by someone in a documentary, video, article, or something like that, and how do you cope with that? Oh my goodness, yes, is the answer here. Maybe this is just obvious, but certainly I've learned empirically through experience that once you do some communication in the public sphere, once other people read what you write or listen to what you say and then talk about it, you will constantly be misrepresented. It happens all the time. People are constantly attributing to me, not only misrepresentations of what I said, but literally the opposite of things that I would say all the time. People say that I think that there's no more reason to take evidence and observation into consideration when we do science. People have said that I think it's possible to mathematically disprove the existence of God. People say lots of crazy things. What are you going to do? Most of the time, the people's audiences are relatively small and life is short, and I don't bother, to be honest. Like, you can't run around. Sometimes I get emails from someone saying, someone wrote an article or someone published a video that misrepresents something you've said. Yeah, life is short. I try to be clear in what I say, I knew when I started talking about the fact that the laws of physics underlying everyday life are completely known, Everyone was going to misrepresent that. And indeed, they do all the time. And I don't mean the person I just responded to in the AMA, but some people get it really, really wrong. And, they just willfully misunderstand in ways that I knew they would misunderstand. And I said in the article, please don't misunderstand it in the following way. And they do it anyway. Because, I'm making fun of people, of course, but look, we're all finite, right? We all have limited capacity, both to read things and to understand them and to talk about them and so on and so on. And that I'm included in that. When I talk about what other people say and have said, I'm sure that I cut corners and I misrepresent them, not intentionally, but, I have ways of thinking, and if I'm trying to understand someone else's way of thinking, it's generally going to fit into pre-existing categories in my brain. And sometimes that fit does violence to the original idea. And so it's very natural that people misunderstand. That's not an excuse. You shouldn't get away with it just for that reason, but I get why it happens. And so, the solution is just that all of us should make good faith efforts to be honest and accurate when we are saying things when we're attributing views to other people, right? I try to be clear myself. I try to anticipate ways in which I can be misunderstood. And what else can I do? I'm not going to chase around everyone who misrepresents me. If it becomes someone famous, then maybe I will, explain on social media or whatever that was a misunderstanding. But, if it's just everyday things, certain punches you have to roll with. Like someone said on Twitter recently, you have to pick your battles. And then the joke was, wait, no, that's a lot of battles. You're picking too many battles. Pick fewer battles. Put some battles down. I'm very much a believer in that particular philosophy. You have to pick your battles. There's an infinite number of battles. Life and energy are finite. Let's pick the best ones that we can pick. And with that, as usual, thank you very much for listening this far. Thanks very much for supporting Mindscape. I hope you're having as much fun listening to it and thinking about it as I am making it. Have a good month.